In this video, what we're going to be doing is talking about inheritance, a very, very important concept in object-oriented programming. In fact, we have demonstrated inheritance a couple of times throughout the videos in the object-oriented sections for the simple fact that you needed to have some inheritance going on for us to demonstrate the particular topic at hand. But we haven't yet had that official lesson on inheritance. So here we are with the official lesson. Inheritance. Now let me go ahead and give you a quick warning. There is going to be a lot of writing in this video, and because of that, I'd like to remind you that your player does most likely have a track bar. You can grab that track bar and move forward at any time while I'm writing out code so that you can get back into the good stuff quickly. I feel it's important to write out a lot of these examples because it allows me to go back through and scribble all over the place as I'm explaining exactly what's taking place inside. Also, this might be a good moment for you to pause the video and go grab something to drink. Some coffee, a Coke, whatever, because like I said, this video is going to be, well, probably pretty lengthy. Alright, with that said, let's go ahead and start talking about the objectives that we need to get through in this video. There are 7 different things that you need to have a clear understanding of by the time we reach the end, and they are, first of all, what is inheritance? Obviously, that's pretty important. After we take a look at what inheritance is, the next thing we need to do is talk about why you'd want to use it. Why use it? After we have that out of the way, the next thing we're going to talk about is syntax. You have seen this syntax before when we've talked about creating classes, but now we're finally going to get to talk about that class-based specification part at the end of our class definition. Okay, so syntax. The next thing we're going to do is take a look at some inheritance terminology. To make sure you guys are up to speed with all of the lingo that's thrown around in the world of inheritance. From there, we need to start discussing member accessibility because it becomes quite important when dealing with multiple classes that build upon one another. So, member accessibility. Next, constructor execution. Actually, Logan, I'm going to go a bit further. I'm going to say slash parameters. And just so that nobody gets confused, I'm referring to constructors that take parameters. Now, we've already taken a look at constructors, but now we're dealing with multiple classes that are, well, inheriting from one another. And having a clear understanding of how the constructors actually fire becomes quite important, as well as what you need to do when a constructor from a base class requires parameters. From there, we're going to touch on casting. Now, casting is not going to be anything new to you guys for the simple fact that we have had lectures over casting in the past, but now we're going to start getting into casting from one object type over to another, and there are some rules in place and some things that you need to keep in mind, and there's definitely some potholes that you can step in that you need to be careful of, so we're going to go over all of that. So that is what needs to be covered in this video. So like I said, there's a lot of things to talk about. So let's go ahead and get started with what is inheritance. Now listen very carefully. Here comes a strong definition of it. Inheritance. Inheritance is a method of creating a class that is based off of an existing class. Through inheritance, this new class that you just created, which is known as the derived class, inherits all of the accessible class members of the original class, and that original class is called the base class. Now, this derived class can then have new functionality added. At this point, you can say that the new class is an extended version of the base class. Now, it is inheritance that gives us the ability to create a hierarchy of classes. Because obviously if we start off with a base class and then we derive from that into a new derived class, we now have a very simple hierarchy in place. We have a parent-child type relationship. So here's what I'm talking about. We've picked on game items so many times. We're going to continue to pick on it here so that you guys are in familiar territory. If we start out with a game item class, we can then, depending on how the class is set up, inherit from it. And we can inherit something like enemy. Okay, now, due to the way that the UML has been set up, okay, the Unified Modeling Language, let's go ahead and switch this around.
I was wondering about that.
Yep, nope, I wanted to draw that because we are inheriting, so of course you're going to see we're deriving this class. But check this out. I just wanted to make a big deal out of it because a lot of people that are completely new to inheritance, when they start flipping through books and they see the arrows pointing the other way, they're like,
well, why does game item inherit from enemy?
Exactly. They get confused. So I wanted to draw that way because that's the way you first picture it, but let me show you another way to read it. Enemy is being derived from game item. Okay? So game item, this, based on the description that I just gave you, is a base class. And the enemy class is a derived class. Okay? Now that's all fine and dandy, but why do we want to do this? I mean, we haven't been doing it throughout all of the coding that we've done so far. Okay, there may have been once or twice we've thrown it in way back. Actually, did we ever do it back in Hyperion? I don't think so, thinking about it.
I don't think, no, there was no complex inheritance.
Nope.
If you look into what everything in C# comes from, that would make sense a little bit.
Yes,
but I mean,
it would. Because everything inherits in C#. Every class you guys have made, even even game item inherits. But we'll get to that in just a minute. But yeah, I don't think we've actually done any inheritance in our application.
Other than the lessons preceding this one, I don't think we've really touched on it too much.
So that brings up a fantastic question. Why do we use this nifty little ability? Well, simple. Inheritance prevents the need for redundant code, and it provides a higher level of organization throughout your program. That is so important. It really, really does eliminate the need for retyping code, and that's a really big thing. It's the promotion of code reuse. Okay? Now, this is all accomplished through the hierarchical creation of classes where higher level classes represent generalized ideas by containing common members that are then inherited and used by deriving classes for more specialized use. Okay? Taking a look at game item and enemy. What the heck am I talking about in regards to more common type members? Well, an enemy would need a position. A player would need a position. Other items in the game, they're all going to need positions. So why recode position in enemy, in player, and everywhere else, where we could put position back here in the base class? So if we added a position member, position can then be inherited by enemy. And wow, enemy suddenly has a position. How convenient. It kept us from having to rewrite code, and that's very important. And then the whole idea of having everything organized, well, just look at this. We can quickly look at our code and see that, well, enemy is being derived from a game item, so that makes sense logically. In the real world, it's like we're doing real-world modeling here. You have a whole bunch of pieces on your table, Monopoly pieces. Well, they're all game items. Now, they're different game items, but they are all game items. So, you could take all of these pieces, and let's say you had some sort of container in your Monopoly box for you to store all of these in. You'd put all the game pieces in the game item box and put that back into your Monopoly box itself. It is a way of keeping all of your pieces organized. Well, the same thing's taken place with code here, and that becomes really important when you start dealing with really large applications.
Right, because as you can see there, the idea of having position in different things. You were mentioning player and enemy and other items all having to have position. The idea is that if position originates from game item, that way if you have 3 classes or 1,000 classes, you don't have to rewrite position 1,000 or 3 times because it's already been defined. It's been reused in any derived class.
And you made another great point without even realizing it. And by having, let's say, thousands of classes, if you weren't using inheritance, they would all be at the same level. Wow, what a nightmare to have to dig through all that.
And you'd have, what would end up happening is you'd have a lot of very similar classes that all had pretty much the same code in it, only differing slightly class by class, yet you'd have the same complexity in every single one.
But by setting it up in such a way that we have these class hierarchies and we utilize inheritance, now suddenly these thousands of classes all belong to these hierarchies, and these hierarchies represent ideas that go from generalized to more specific. And that helps keep everything very organized while, as Logan was just saying, keeps you from having to retype code. We can reuse code, and that is obviously important. Now let's visit this whole generalized and more specific thing that we're talking about. What are you referring to? Well, first of all, let's just take a look at the real world. I think everybody that's watching this video is going to be familiar with what teachers are. Now, I just said teacher. I didn't say anything specific. I gave a very generalized term. So let's write this down. So a teacher. Now, that's generalized. So let's do this to make this a little easier for those that are following along with notes. All right, so generalized. Now let's get a little bit more specific, so less generalized. We could have, let's say, an English teacher. Perhaps a math teacher. And let's see. Pick on somebody else. How about a science teacher? So this whole row is a bit more specialized. It's a bit more specific. So we could come in here and simply say that this is less generalized. Okay? But even this can be presented in a more specific way. Let's pick on, let's say, a math teacher. We could have, branching off of this, a preschool math teacher. Or we could have, let's say, a university math teacher. So now you can say we've got very specific. So we started out with a very generalized concept, a teacher. Now, in the real world, we all know a teacher is going to be something very specialized, but just saying the term loosely, a teacher, is just an abstract idea. It is an educator, and that educator is going to have some very common behaviors that will be found throughout all teachers. They should all know how to deal with students. They should all know how to prepare lessons, to present content, etc. Okay? But that's very generalized. That can be completely different if you're a science teacher in the lab when comparing that against a math teacher who's got to perform some crazy explanation of a formula on a board. Okay? Or a shop teacher who's going to teach you how to work with wood and prevent you from cutting off your fingers. There's no teaching you how to keep your fingers from getting cut off in a math class because that's irrelevant. Okay? So the teacher is going to have these very generalized concepts in place. But now as we go from teacher to something that's more specialized, less generalized, such as English teacher, science teacher, and math teacher, now we focus a little bit. They inherit everything that teacher has. They all know how to prepare lesson plans, present content, deal with students, etc. Excellent. But now an English teacher is going to know how to prepare English-type lectures, where a science teacher is going to know how to prepare science-type lectures, and a math teacher is going to know how to prepare math-type lectures. Very specialized at that point. But we get even more specific as we then come down, as the example we presented here, all the way down to preschool math teacher and a university math teacher. A preschool math teacher has no business teaching high-level calculus to those poor students. Why? Because they're going to sit there, drool, stare at the board, and be confused and lost. That's pointless. So there's no need for the preschool math teacher to have an understanding of this super high-level mathematics because it's not going to be used. But now the university math teacher needs to have, well, high-level skills. And this is where we really get into a very interesting world. Depending on how you want things to flow, you're going to find yourself most likely laying out class hierarchies like this and then going, the more I think about it, check it out, Logan. This is a really good example right here. The more I think about it, the preschool math teacher, he needs to know all the basic mathematics. A university math teacher better know all the basic mathematics and then know all of this complex stuff that he's got to teach. So we could do this. We could redesign our tree here and have a university math teacher down here.
And we would do that if we found a lot of things ending up being common between preschool math teacher and university math teacher. If it didn't make sense to move those all the way back into math teacher for some reason, we needed to have them outside of math teacher. But we found a ton of things in preschool math teacher that were the same thing in university math teacher. And basically what ended up happening is a university teacher ended up being just a more complex and more specialized version of preschool math teacher. It would make sense to inherit from preschool math teacher so that we don't throw away all the basic concepts when defining the complicated ones.
Exactly. And what do we have here? We have very specific. Where a university math teacher will have inherited everything that a preschool math teacher can provide, where that had inherited everything that a math teacher should be able to do, period, where from there we had inherited, well, all of the basic traits of a teacher.
Yeah, and there with the university math teacher, we had decided that the university math teacher still needs to know how to count. So we decided to switch over to using preschool math teacher.
That's right. So this guy right here ended up being derived from, so I'm going to throw my arrows in there. He just ended up being derived from the preschool math teacher. The preschool math teacher was derived from the math teacher, which was derived from teacher. The English teacher was derived from teacher, and the science teacher was derived from teacher. Now check it out. Because we're now using inheritance and we're promoting code reuse, how convenient will it be later on to, well, we've decided to add a shop teacher to the whole program here at our school. Well, excellent. The shop teacher needs to know how to deal with students, how to prepare lessons, etc. So now he can just come in here, shop teacher. And by simply just creating this class and have it inheriting from teacher, but we haven't coded anything else. If we were to instantiate a shop teacher, he automatically knows how to put lesson plans together, deal with students that raise their hands, or deal with rowdy. He has all of that ability, just that fast. We just simply said, look, make a shop teacher, inherit from teacher. And boom, everything that teacher has that is accessible is now within the grasp of the shop teacher. Now, of course, we would want to add to the shop teacher, make him aware of machinery and the tools that he's going to be teaching students to work with.
But that's the key. When we start with the shop teacher, we can immediately begin coding things like working with machinery. We don't have to worry about how to make lesson plans or any of the basic teacher stuff. Exactly. That's already there. We're already using it because it was already in teacher.
Could you imagine all the code if we were going to create some sort of teacher simulation program? All the code that would be involved with dealing with simulated students, lesson plans, presenting, all this stuff. Well, we'd have to reproduce that code with each of these teachers that we added. That'd be awful, wouldn't it?
Right. It would end up being a management nightmare because what would probably happen is you'd write the one teacher, and then to save time, you'd probably just copy that code into a new file. So it would seem fast. Like, oh, cool, I made a second teacher, and it took me 5 seconds. Sure. Great. You start adding on to it. and then you copy a teacher again into something else. And great, that still took only 5 seconds.
And then later on in time, we suddenly had let's say a blind student that is going to be taking your class, and now we need to know, and that blind student is going to be in the English class, so we need to know how to handle the particular student. It needs to be able to read Braille and all this stuff, so we've got to handle this particular situation properly. So we go into the English teacher and we make those changes, but we forget about the other teachers. And now this particular student, Joey shall be his name, ends up signing up for SHOP next semester. Well, SHOP, we forgot to copy and paste that code over in SHOP.
So now all the work that we had to do in the first teacher, we have to now pour it over to the second teacher. And at that point, we're probably going to look at the rest of them, knowing that this was a problem. We need to prevent this in the future. So now we have to go through all of the teachers we have, which could be 4 or 10. It all depends on how many you have. But still, you're doing the same redundant work to a lot of other teachers.
That's right.
What if a bug was found back in just the core teacher code? What if the lesson planning code was backwards?
Okay.
Or any other random bug.
Okay.
Now you still have to, once again, in that case, you immediately know that, well, we have a bug in all teachers. That first code that we copied from actually has a bug in it. Now, how many teachers have we made? Well, it's been 5 years, and we've made 50 different teachers.
Oh.
So now it's a matter of finding each teacher one by one, finding that same place in code and changing it.
Yeah, so
whereas if it could inherit, we could find a bug in teacher, and that's the only place that bug exists.
That's
Fix
right.
the one bug, and then that's just it. It's done.
So a complete nightmare if you did not have the ability to implement code reuse quickly, which is a very strong benefit of inheritance. In fact, in my opinion, it is the key thing we get from inheritance. Okay, so now that you have this very basic understanding of going from a generalized concept to a very specific, so from generalized, and as we worked our way down the hierarchy, we got very specific. What I'd like to do now is pull up a new screen, and let's all just pretend like we're putting a very simple game together and design something and show you how you can go about. And this is not Design 101. This is Design Sub 101, okay? But it's just to give you a very generalized idea of how you can go in here and start laying out classes. And we're going to pick on things that we're all familiar with. That's right, game item, etc. So let's go ahead and jump into a new screen. And in here, let's say that we have a few items. So here's a more focused example. We start out with, let's see. How about we have an enemy? Because we got to have enemies in our game. How about we have a player? Wouldn't be no fun if we couldn't play it. It would just then be a demo. Let's say, all right, let's do something a little different than we've done in the past. Let's say that we're going to be fighting on some sort of terrain against our enemies. And we've got some rocks, and let's say there's trees. So we actually have some things in our environment other than just enemies and ourselves. Sound good, Logan?
Yeah, sounds good, because, I mean, you want to be able to populate things that are maybe taller than the terrain or exist on top of the terrain.
Precisely. So here we go. We've got 4, that's it for our game. We've got 4 different things that are going to be in our game. We're going to have rocks and trees. We can hide behind the big rocks and the trees, which is excellent, and fire around them, and our enemies can do the same, and we're going to be battling the enemies. So that's the idea. Now, how do we want to structure our classes utilizing this new concept of inheritance that we now have a beginning understanding of? Here's how I want to do it. Let's just ask ourselves, let's just do some general observations. And this really is important, guys. All right, so I'm going to come in here, draw a little line down there. All right, first of all 4 of these guys, what do they have in common? Well, for starters, how about we just say that they're all game items? Right, Logan?
Well, just from an English sense, they are all items that are going to be part of this game. So in that case, let's make a base and let's call it game items.
All right. And that's the key here. In fact, I don't even want to start talking about bases and all that yet. Let's just do the general observation. So these are all items that I've described that are going to be in the game, so they're all going to be game items. And as Logan said, just basic English here. All right. So now, what else do all of these guys have in common? Well, they all are going to need a position. They all are obviously going to have a position in the world, because if they didn't have a position, then how would you know where to draw it? It wouldn't even be in the game because they didn't have a position, so he couldn't be there. So all have positions. Okay. I'll go for that. What else? All right. How about names? For whatever reason, we want to be able to identify a specific tree or a specific, or even we come up and we bump into it and it says, you bumped into a rock because it knows its name, or you bumped into a tree. So we can give it names. Enemy, you know, you're fighting the spider, you're fighting the zombie. And of course, the player at the very beginning of the game, we're going to ask you to type in your name. So everybody gets a name. All right, so far so good. All right, next. Well, in the world, they're all going to, well, it depends on the type of game. If it's a 3D game or if it's a 2D game, they're all going to have rather a model and texture, or they're just going to have a texture if it's a 2D game. But they've got to have something that we're going to draw, right? I mean,
right, they're going to have something that is going to describe how the item is rendered.
That's right.
Since we're going to say that this is a graphical game, and there needs to be some sort of graphical asset that is drawn to represent this game item.
So we could say that all have and just to simplify this, I'll say a model or texture. And anytime I say that, please understand that I'm stipulating that if it's a model, it has a texture built into it. Okay, so
right. That's just assuming that a model internally handles all the texture stuff. That you can either put a model with this, a textured model with this, or just flat out put a texture with it and do a 2D game like we've been doing.
Exactly. Okay, what else? Thinking about this from just the generalized look, a generalized angle. Thinking about it, that's good enough. They're all game items. They all have positions. They all have names. They all have a model and a texture. It makes sense for all of them. All right, so let's get a little bit more specific then. So let's see. The rock and the tree, they're just game props. As of right now, they're not going to do anything special. So we'll say rock and tree are props. Okay, again, just a general observation. This has nothing to do with code at the moment. All right, let's see. Anything else about the rock and the tree? No, nothing I can think about. All right, let's look at the enemy and the player. Well, obviously, the enemy and the player can get hurt and killed. I mean, the idea of the game, right? So the enemy and the player, they both need help. Makes sense? Because obviously we don't want the rock and the tree to have health, because they're just going to be cover for us. That's all in the game that we're implementing here. I mean, obviously you could design a game where the rock and the tree has health.
But I mean, most games don't. And most games, when you come across a rock or a tree, you can just take it for granted that you're probably not going to be able to destroy it, no matter how cool that would be.
All right, let's think about this. All right, so what else they have? Well, if they have health, the health needs a way to be diminished. So they're both going to need to have some sort of take damage type property. So again, it'll be enemy.
Or rather, both enemy and player are damageable.
Yeah. And player are damageable. Probably missing an E in there. I don't know. Anyways, there you go. 7, 8. Okay. Let's see what else can we do. Enemy and player. That's good enough. We can keep that generalized to that. All right, let's look at the enemy himself. I know some enemies are going to be really intelligent, and some enemies are going to just be like grunts that aren't very intelligent. So the AI system for these guys would need to know what kind of IQ they have, and based on the IQ, it can make the appropriate decisions on how they're going to act on the battlefield. So enemy has an IQ. Nice. All right, let's see what else. I know, and the player doesn't need an IQ. That's up to you. You're the player. You demonstrate your own IQ. So another thing that the enemy could have. How about this? Kind of works hand in hand with its IQ in a way. The enemy has a retreat health, meaning that he starts off with, let's say, 100. And then you're shooting him, and it gets down. He gets down to 20. And that happens to be this particular enemy's retreat health. At that particular time, his only goal is to retreat because his health is so low he knows he's about to die. And that would, of course, simulate the enemy having some, intelligence. He's worried about dying. So let's put that in place. That sound good, Logan?
Yeah, that way it'd be kind of like a threshold where after a certain amount of damage has been taken, the enemy will decide to give up the fight and run away.
Yeah, I like that. We could probably come up with a few more, but that's good enough so that we don't end up with too much code. Now check this out, guys. We're going to go from generalized to very specific. And we've done just that, haven't we? We've started off here, and as we've worked our way down, with my amazing drawing skills, to specific. Okay? Everything's a game item. Well, let's come up here and do some more drawing on this. So everything up here is a game item. Okay? Sounds good?
That was determined in observation 1.
Yeah.
All things are game items. So you could say that, well, if we circle all the things that are game items, we'll circle everything.
All right. Then the next thing we said was all have positions, all have names, and all have models and textures. Okay? Well, let's come over here and start building something. So I could say game item. And game item is going to have, find some way to draw all this. He's going to have a position. He's going to have a name. And he's going to have a model or texture. I'll just call it text. All right? And that's our game item. So you see it has a position, it has a name, has a model texture. So all the way to this point right here, we're very generalized. Okay? Now we're going to start getting a bit more specific. The rock and the tree, they're just props. Well, these two guys, that means we have just managed to bunch them together. So props. So how about we have props extend game item or be derived from game item. That looks good. Now, we didn't decide on any additional functionality whatsoever. So the interesting thing here is we're going to have props with nothing in it. But what's nice about doing this is we've set ourselves up later that if we want props to have some sort of built-in functionality or behavior, it's now our framework is set up for us just to go in there and modify props, and then props will just start working appropriately. If we had not put props in here, then who would we have to modify to give props some sort of behavior? We'd have to modify game item, because if we don't create instances of props for our rocks and trees, we'd have been creating instances of game items for our trees and rocks. That means we'd have had to add the code into game item, but that meant all of a sudden our enemy and our player would have got that code, and that may have been irrelevant.
That also means that in the future, if we decide that props have any special functionality or attributes, for example, what if we said that enemies are able to take cover? In a future upgrade to the game, we upgrade it so that enemies are able to take cover behind props. Mm-hmm. That might mean inside of a prop, we could add something like how well hidden something is, like how much cover a prop contains.
Exactly.
We already have props defined. That way, we don't have game items set up where enemies are trying to hide behind each other because they all think they have cover.
Exactly.
Instead, we've already defined the class of props. We can tell what a prop is. It would make sense that props provide cover, so that an enemy could use that based on props.
Exactly.
It gives a place that would make sense to add the code.
Exactly. Okay, so let's go ahead and come in here and draw another line. because that is the end of props for this particular implementation of our little game. All right, so now we're dealing with the enemy and the player. Now, they both need help, and they are both damageable. They both need the ability to take damage. So we've just grouped these guys together. Now, generally in the past, we've talked about an enemy inheriting from game item. But in this particular case, why would we want to come in here and check this out? Make an enemy and make a player and have both of them derive from here when they both share common things. In this particular case, they both share health and they are both damageable. So would we want to go in there and and derive from game item into their own separate classes? No, because we want to keep this thing as modular as possible. We want to keep all of our classes as generalized as possible as we head down the path toward becoming more focused or more specialized. So we can group these guys together. So let me just come in here real quick and see if this guy will let me undo. Hey, fantastic. So what I'm going to do is take enemy and player, and I'm going to group them up here in our little chart. So nice little grouping. All right, now we need some sort of name that makes sense here. Now, we called this guy props. So how about we call this guy, we've hinted at this terminology in the past, pawns. Picture a chessboard, bunch of pawns, okay? So pawns are going to have health and take damage. So now let's come back over here and revisit our hierarchy that we're drawing out. So pawns are derived from game item, and they are going to have health and the ability to take damage. And that is a method, so I'll put open and close and parentheses in there. You just got to look kind of close. All right, fantastic. Now, that allows us to come back over here to our general observations and draw another line. Hang on. Let's draw that line up just a little bit. There we go. All right, oh, check it out. As we are following our generalized to specific arrow over on the right-hand side, we are indeed becoming very specific. At this point, now we have an enemy which has an IQ, and so now we're dealing with just a particular class, an enemy class. So, and we obviously need a player class because, well, we saw that up above. So at this point, here's what we would have. We would come in here, and instead of just instantiating pawn for all of our enemies and our player, we'd want to break them up because the enemy has an IQ and the enemy has the retreat health behavior, and a player, well, that's up to the real player that's playing. So we could come in here and say, all right, we're going to have an enemy, and we're going to have a player. So we split these guys up at this point. And the only reason we did this is so that enemy could have IQ and retreat health. And that's retreat health, okay? So we all agree on that. Now, player didn't need those things. You'll notice up under props, we didn't extend off that into a rock and a tree because rock and tree, they don't do anything. They're just a prop. So all we need to do is instantiate props, set its model to a rock, set its position to where it's going to be, set its name to rock, and we're done.
Because the idea is that we use them basically like game items. The only difference is they are classified as props, so if we should ever want to put any type of prop-specific code or functionality, we have a place to do it.
And how convenient. If we want a bush in there, all we got to do is, we don't have to extend anything. All we got to do is instantiate props, put a bush model into it, put its name as bush, and set its location in the world. So this guy is very specialized for what we need. And in all reality, what is he? He's just a game item. But once again, as Logan said a few minutes ago, we've set this up in such a way that we can come back in later and add to props if we want to add any sort of additional functionality to props. Player in the end is just a pawn, okay? That's all we needed in this particular case. We did not want to instantiate enemies and players from pawns for the simple fact that we needed the enemy to have an IQ and a retreat health behavior. And we didn't want player to accidentally pick those things up. It'd be just not necessary.
Right, they would be unusable on a player because IQ and retreat health aren't going to influence how a player works. Instead, you'd have something more like mouse sensitivity, something that would actually make sense to how the player works.
Precisely. So this is how we ended up breaking it down. We just simply took pawns and derived from it two different classes, enemy and player. And now, even though player doesn't have anything now, in reality, we could go in there and we could add, go ahead.
Yeah, in reality, what we'd probably do is start adding input code.
That's right.
The ability to respond to the mouse, the keyboard, or any other control device.
And obviously, you wouldn't want your enemy to have that kind of stuff because the enemy is going to be controlled by some sort of AI. And the player needs to be controlled by, input into your computer that you're going to be interfacing with while playing the game. So by splitting these up, we have the ability now to go and put very specific code into each of these classes. But let's stipulate that position, name, and model and texture, which comes from all the way up at the top of the hierarchy from game item, they are all accessible to all derived classes below. That means all derived classes will inherit, so there's inheritance, those members. So as we worked our way down all the way to player, if we were to take a look at player would have, actually let me do it a different way. If we were to instantiate player into player with a small p, so the player, we could say dot and what would be available to us. Let's stipulate that everything was public. We would be able to set its position. But position was defined all the way back up on game item. That's right. But it inherited all the way down to the player class. So we would have dot position. We would have dot name. We would have, let's just say that this is a 3D game. We would have the model. We would have health. And we would have take damage. And let me put a capital T over there. It made me feel better. There we go. And all of these, of course, is player. How cool is that? Because of inheritance, each of these classes that laid out basically just a very generalized concept, what they had were then inherited by classes that started to become a bit more focused. And that just continued its way all the way down to our final classes. Okay? Logan, is there anything you want to add to this?
It almost makes it look like the usage of player is such that the hierarchy is flattened when you make a new one, because inside of player, you have anything that was accessible that was inherited.
Exactly.
So it looks like we have just a player that has many things, like position, name, model, health, and take damage, when all that was defined in player itself was nothing. Pawn had 2 things and game item had 3 things.
Yeah.
But again, once we start to actually instantiate and use an instance of player, it's like we can flatten the entire hierarchy, look back through it, and see everything that was made available.
Exactly. Now this does come into accessibility, and we'll talk about this shortly, but you guys have been playing with modifiers, access modifiers, for quite some time now. So you're very familiar with public, protected, private. Protected you're familiar with, but you've never really used. Now you're going to get to use it. But public, internal, and all that good stuff. So those are access modifiers. And accessibility, man, those modifiers become really important when you start designing class hierarchies like this. Okay, so let's go ahead and jump back over here to this guy and scroll back up just a little bit and take a look at our objectives. So first of all, what is inheritance? Let me also make sure that focus is properly set so that I can actually write on this level. So starting out with what is inheritance, I say that's pretty much covered. Why use it? I think we've covered that pretty well, Logan. So now it's time for us to take a look at syntax. All right. So let us go ahead, come back over here, create a new level or new layer, and hide out some of this stuff. And let's start taking a look at syntax. Now, syntax is nothing new. You have seen this before. It's just now we get a focus on it a little bit better. So the syntax that I'm going to give you is class syntax, how to go about defining a class. So you have seen this. We start out with modifiers. Again, this is basic syntax. I'm dropping attributes for now, for those of you that know what I'm talking about. All right, so modifiers, then the keyword class, and then the identifier, the class name. Then optional, our base list. And then we're going to have an opening curly brace, and we'll have our class body, and then our closing curly brace. And optional, for those of you coming from certain other languages, the option to put a terminator at the end of the whole thing. All right, so our focus here is this section, which is called the class base specification. All right, so the class base specification. Now, the first thing you need to know about class inheritance is that it is what is known as single inheritance in regards to classes. We are only able to inherit from a single class, meaning we can only inherit from one base class. Now, that doesn't mean that we're limited in C#. There are ways when we start working with interfaces that inheritance becomes even more powerful. But that is for a later discussion. That's when we start talking about interfaces. But for now, we're dealing only with deriving from classes. Okay? So, keep that in mind. Single inheritance, a class can only inherit from one class. Alright, so, but of course, now you can have another class inherit from that class, and another class inherit from that class. It's just that each class can only be derived from a single base class. But as you saw in the hierarchy that we drew a few minutes ago on the whiteboard, that we could have, well, a hierarchy of multiple classes that are all basically, helping create this hierarchy.
Right, but only one class can inherit from only one other class at a time. You can't have like a flat level, this class inherits from everything else.
I'm a visual person. You can have this. You cannot have this. Okay? This is a big no. Can't have that, okay? Again, there's ways of kind of simulating this behavior, but that gets into inheritance, or excuse me, into interfaces, and we'll be discussing that a little bit later on. Okay, so let's go ahead and turn our attention back over to our syntax. So, a very simple example based off of how, let's just say, enemy and game item, because those are the two common things we generally pick on. Let's just say, I'm getting away from my example for just a minute that we were doing a minute ago with our little mock-up game, and just go back to the world of we have an enemy that is extending game item. So here's what it would look like using the syntax above. So we would see class, enemy, extends game item. And then, of course, the actual meat of the class itself. Now, colon, entire thing, class-based specification, as mentioned up here. This class-based specification is saying that the enemy is a derived class from game item. So when you see that colon, there's two different ways that you can read it, and depending on the mood I'm in at that particular second, I may read it one or the other. You can read this as enemy is derived from game item. That works. You can also read it as enemy extends game item. So there's two different ways that you can go about reading this line, and depending on the mood I'm in, I use both. Okay, so just keep that in mind. I will actually read it that way, both ways, as I'm working through examples. Okay, so that's just very basic syntax. Now, what I'd like to do is let's go ahead and pull up another whiteboard real quick and make a very simple game item and enemy program and then show you what's taken place over in the heap, because that's really important. This is where you're, for the first time, going to start getting a clearer picture of what takes place with instantiation. So let's go ahead and come in here, create a new whiteboard. Let's hide that, hide this. All right, very nice. So, simple game. So this is where you guys can grab that track bar and move forward if you would like. I am going to create a class that is called game item. And inside this class called game item, I'm going to have a public vector 2. Logan, by the way, when I have you code this out, just keep in mind you will need to make sure that you make reference to Microsoft's XNA framework, because we're going to start using vector from now and get away from point. And position. Terminator. And let's have a public string name, because we've kind of been adding name into all of our game item pieces. All right, now let's say that these are the two things that are common throughout all game item types. So now let's get more specific. Let's make an enemy. So we're going to extend the game item class to make it more specialized, more focused, by saying class enemy extends game item. All right, inside here, let's go ahead and get my pen over there. Let us have a, we'll use some of the pieces that we did a second ago on the other board. Let's have a public int IQ. Let's have a public I know we'll do the retreat too. Int retreat health. Okay. And we could go ahead and put some functionality, some behavior into this as well. Let's do a public void, because we're not going to return anything, show info. And what's the behavior going to do? Let's have it write out name and IQ. So I'll just put name, IQ. But Logan, you know that means right. Okay, and we'll go ahead and close that off, and we'll close the class off. All right, two different classes. We have a base class, and we have an extended class, or we have a derived class. Now, if we wanted to, we could come all the way back up here and say something along the lines of enemy. This is back in the main method. And let's just create a spider. Equals, and we'll call upon the constructor, the new enemy. Well, you got to love when that happens, right? All right, and then from there, let's go ahead and set some stuff. So we could say spider dot name. This is the scary spider X once again. So that's his name, X. And then let's say that the spider's IQ. Did it as caps, I'll do it as caps here. He's not. He's pretty sharp. Yeah, let's do that. All right, so we'll set it to 120, so he gets around, and then let's just show that information out. Terminate. So once again, this stuff right here, as we continue to have Photoshop be so kind and auto jump me up and my pen gets to the top. This is all in main. This is our base class. And then let's go ahead and scroll down just a little bit. And then here is our derived class. Now, let us take a look at what is happening in memory when we do this. We all know that our objects truly reside on the heap. So that means we've got to draw out a heap. And then our local variables will reside on the stack. So we'll draw out our stack. And I'll just make a small stack. Okay, I'm not going to worry about creating the object type and all that good stuff as we've done so many times in the past. But we know that they will actually... alright, I will. I'll just draw out two. Logan found that funny. So we have a game item, and we have an enemy with all their good stuff. But check this out. We're going to instantiate. We're going to create a spider, right? When you create spider, what really happens when we create an instance of a class? Well, we know that the object then gets created over there. But in this particular case, we get something a little bit more interesting that takes place. Instead of what you're probably expecting to see, because what are we instantiating? We're instantiating enemy. Well, when you instantiate enemy, you get an instance of every single class all the way back up the hierarchy. Okay? So we would have enemy. Let me see if I'm going to have enough room for this. Let me do it this way. Let me get that out and that out. So we'd have enemy. And we would have our game item up here. Inside game item. This is where things get really important, guys. Inside game item, we have position and name. And inside enemy, we have IQ. Oh, this is going to be a little tight. We have retreat health, which I'm just going to call r.health. And then finally, we have some behavior, which I'm just going to draw a box right there. But where does the behavior really reside? Back in the object type. So our behavior is back over here in our method lookup table. So this is where we're going to find show info. Okay? Because we know how to get back to our actual types, if you will. Okay? But what we have just created right here is an instance of game item. Or I'm sorry, of enemy. So what does enemy really look like? Enemy really looks like an instantiation of every single class that's involved in the hierarchy. So everything above enemy, okay, gets instantiated. So right here, we are actually looking at, it's almost like we're looking at two instances. It's almost like we're looking at two objects. But we're not. That is so important to understand, critically important. Let me go ahead and erase. Everybody now knows this top part is game item, the bottom part is enemy. But here's what's critically important. Spider just points to this thing as a whole. He's referencing the whole thing. The whole thing consists of an instance of enemy, an instance of game item, and an instance of object if you want to go one step further back. What are you talking about, instance of object? We'll talk more about that in just a minute. Now, That is very important to understand, which means in the scenario that we had a few minutes ago where we had created a game item, we had a pawn, we had an enemy. If we were to create an instance of enemy, the enemy would look like this on the heap. He is still one contained unit. And this is what the reference points to. This is so important to understand. We can prove this to you later. There are several books out there that, in my opinion, describes this wrong. When we start getting into casting, which will come at the end of this video, I'll talk about exactly how they're explaining things wrong. So you got to be careful with some of the books you read these days. We're pointing to the whole thing, okay? Now, what happens? Well, why do we have all of these instances? That's important to understand. Well, it's because position is maintained back here in the game item instance of the class. The name is maintained back here in, once again, the game items instance of the class. So inheritance is just these guys all being hooked together and the accessibility that is there from our final derived class back up, things that we can touch. Okay? It's inherited in the fact that we freely got an instance of that base class that came along with us and was part of our entire instance. Okay, does that make sense, Logan?
Right. What happens is an instance, while it is you call it a group or a bunch of actual classes get loaded to make up that. It is I don't want to call it a stack because we have the actual real stack.
Right.
But I mean, it is though you have stacked a bunch of instances together, but the key is when you reference them, we have a spider and that is acting as a reference to the instance that is all of these individual classes.
Right.
What that looks like is as though all of those instances have been flattened.
Right.
When you access a part of the game item, you access it in the same way that you would access a part of the enemy. It's through spider. So you could say spider.name and spider.retrieve health.
That's right.
It all looks as though all of these things have all been flattened into one thing, and that's what we call the instance. So that instance, while it is actually these individual classes all being instantiated, when you actually look at it through the reference, it looks like you've flattened everything down into a single instance.
Very nice. And that is absolutely the case here. So this is very important to understand. Now, I've been throwing out the term object a couple of times. All right, let's go ahead and spend just a second and talk about object. Every single thing in the C# language, at some point, everything inherits from object. Okay, object is the ultimate base. So where I have created the game item class right there, check this out. Actually, I'll just do it over here in the actual code. I could say game item extends object. Ignore the casing. Okay? So that right there is the exact same thing as what I just had a second ago when the colon and object was not there. So when we were lacking that class-based specification, doesn't matter. The compiler knows. The compiler knows that every single class, if it does not extend another class, it extends object. So we always have object. It's very easy to prove too, because anytime, like take game item, right? And let's say you instantiate game item into a player. Now say player dot. IntelliSense pops up. There are more things in there than just the things that you define publicly inside of game item. You have things like get type. Where does get type come from? Get type comes from object, and it gets inherited. So that's why when you create an integer and you need to convert the integer to a string, you have the ability to basically take the variable and say dot to string, because it came from above, okay, if you want to look at it that way, because everything originates at object. So when I'm drawing out these graphics right here, you can go ahead and stack one more instance in there, and that is the object instance, though you're not going to see me doing that for every single thing, because the closer and closer we get to what's really taking place on the heap, the more cryptic things would look. I mean, even my representation of object type over here is very generalized at the moment, okay? So that's very generalized. But it does allow me to say that if I happen to call upon the show info behavior, we know exactly in the lookup table where to find it, which from the lookup table, now we know where to go, get that code, JIT it if required, and actually execute it. All right? So it's very handy how all this stuff works. Logan, anything you want to add to that?
No, I think that's a pretty good example of how everything's put together.
So every single thing. As a matter of fact, just to have a little bit of fun with it all, well, I'm going to do this. We'll come back in here, go back to, pick on one of these guys. We'll jump all the way back down to here for just a second. And let's complete this graphic. Object. Okay? Everything. Be it an integer, be it a value type or a reference type. That's a better way to put it. So meaning if you create an int or you create a float, these are value types. Or a struct, which is, well, it's all right, I'm getting ahead of myself. Some of you guys haven't seen yet. All of these things still are derived from object. And same thing goes with all of the classes you define. They're all derived from object. So just keep that in mind. All right? So let's see. Let's go ahead and get out of here, jump back over here. So now that we have seen this, the neat thing about this whole thing was not just to show you what's taking place over here on the heap. And here we got our stack. Though honestly, I think it's very important that you understand how this magical inheritance really happens. The way it really happens is we instantiate every single class involved in that branch or in the hierarchy of the creation of the final derived class. We instantiate all of them and we represent all of these instances in one containment, if you will. And that containment is the instance of the object itself. But now each of these instances can maintain their own state. Globally, though, through the object's point of view, it looks like it's all one state.
I would say that each of those instances adds something to the overall state of the instance.
They do. It all depends on which way you want to look at it.
But that also goes back to the flattening, saying that the game item has position and that is part of its state. If you were to look at it through the reference, flatten everything down, you see the game item's position as part of that state. So in that way, it's part of the overall state. Even though if you unflatten it, look at game item, you say, okay, part of game item state is position.
That's right. The reason I like to say they all, and just so that you guys hear both of our reasons on this, the reason I like to say that they all maintain their own state, but it's still globally perceived as the state of the instance, is because you can very easily, in any of these classes, have private members that take care of maintaining stuff, and down in a derived class, we don't have access to those private members, and that's why I like to think of it as that
I see where you're going with that,
maintaining its state.
You could make it private and then declare a new one, and then you get into a case where the state is in fact different between the actual instances of each class.
That's right. But then, of course, you have the state of the instance, the state of the object itself, okay? So that's the big thing that I wanted to push here. Anytime you have one of these scenarios where you've got inheritance in play, and then you make an instance of the final derived class, everybody involved gets instantiated. And they're all grouped together. So keep that in mind. Okay, so now that we've got that out of the way, Logan, let's see. What do we want to do now? Do we want to show this one? Yeah, let's just show this one real quick. We haven't seen, it's just been me talking, you a little bit, and a whole bunch of whiteboarding. Let's jump over real quick and make this, just so that they can actually see when we call upon show info, that we'll actually see the IQ. And so what are we asking for? We're asking for the name, and we're asking for the IQ, but these are where? They're actually up here in the instance of the game item itself. Okay, well, actually, no, they're both. We've got one of them there, and we got one down here. How cool is that?
So that really shows that whole flattening mentality. While each of those one was part of game item, one was part of enemy, but we can access them both from the reference from Spider.
Exactly. So let's build it real quick and just show them what happens on the console.
Okay. To do that, let's start off with a console app. And then once that loads up, we can move on and define our classes.
All right, so we'll start off with the first class, being the game item class.
All right, this will be class game item.
And go ahead and add a reference to XNA real quick.
Oh, yeah, because right now we're going to need vector 2. Vector 2 comes from XNA. So
I'm sneaking this in there as much as I can just so that they get more and more comfortable
as we hinting at bits and pieces.
That's right.
So what it comes down to is we need to add a using so we can access the namespace.
But we got a reference.
But we can't access that until we add a reference to our overall project. So I'm going to come over to the project, which is console application 1, right-click on reference, and go to add reference. Inside of add reference, once that loads, we'll jump down to Microsoft.xna.framework. We'll say OK to add the reference, and there it is. Now we can reference the namespace using a using statement. So using Microsoft.xna.framework.
Okay.
And there we go.
Now let's rock and roll. So going down inside of game item, we've got two members to define: a public vector2 position, and then we've got a public string name.
Right, so public string name, and just out of pickiness for the casing, because they're public, I'll make them capital.
Okay. Now let's go ahead and jump down and create an extended version of game item called enemy.
Okay, so this will be class enemy extends or derives from game item.
And here we've got 3 class members to add. 2 data members, so 2 fields. So let's go ahead and do a public int IQ. And let's do a public int retreat health.
Okay, so that will be retreat health.
All right, now let's add our behavior into it. We've got one public method, so it's going to be public void show info.
We've got show info, and that is going to write some stuff out.
Yep, so console.writeLine.
So console writeLine. And there we go with spelling.
And then we'll say that name equals, and then we'll just append name to it. And here's why I wanted Logan to actually type this out. Watch this, guys. He's going to say plus and type name. Look at that. There's name right there. Proper casing and everything in IntelliSense. Notice he didn't have to do anything like game item dot, or he just referred to it as if it was originally actually defined inside of this class, because we've inherited it, okay? We just have regular access to it.
Right, it's even called string gameitem.name if we were to hover over it.
That's right.
So the system knows that it's coming from game item, but since an enemy is a game item, and being a game item, it has a name.
That's right.
And therefore, inside of enemy, we can directly access name.
Exactly. All right, so then the other one, go ahead and write out the IQ.
We'll do the same type of thing, like IQ equals, and then we'll add onto that the IQ. And if we look at IQ a little bit more closely, we can see that that is, hang on, let me get the tooltip, int enemy.iq. So this is something that we're getting from the fact that we're an enemy.
Exactly. But name and IQ, we've just treated them as if they were brothers. That's the cool thing here. All right, so now let's go back up to our main method. We'll wrap this whole thing up with a quick demonstration of an instantiation of enemy. So let's go ahead and create a type would be enemy, spider, equals a new enemy.
All right, new enemy.
And we all know that this is going to create an an instance of everything in the chain. Okay? So we get an instance of what? Enemy, game item, and object. All right, so now let's go ahead and turn around and take spider. Since everything's public, we can just access it directly through our reference. So spider dot, and check it out. We've got IQ, name, position, retreat health, and show info. How convenient. Let's go ahead and set its name to X, following the example. Okay, and let's set its IQ to 120.
So spider's IQ will be set to 120.
And we're not going to worry about position because we're not showing that out with our little show info method. So let's just go ahead and call upon its behavior of show info. And now let's do a read line to halt things.
All right, simple console read line. And let me space this out a little bit, and now we're ready.
Okay, so again, a very simple inheritance scenario. Since everything is public right now, we can just come in here and instantiate enemy, and with the instantiation of enemy, we can access everything. And then when we turn around and we call upon show info, it's just going to spit out name and IQ as if it was just all in enemy to begin with. So let's go ahead and run it. And so coming from enemy, we have name equals X and IQ equals 120. So that demonstrates that we have inherited the name member coming from game item. Okay? Logan, anything else you want to add to this?
Nothing I can think of.
All right, very cool. Let's go ahead and just close that window. Let's keep the code up right now. Let's jump back over here real quick. Now, the next thing I'd like to do, if we spin just a second and come back to our... Let's come out of here. I'll make this a little bit bigger for a moment. come back over to our objectives. At this point, we've now taken a very good look at syntax with some actual coding examples. Now let's go ahead and move over to terminology. All right, so with that, let me go up here to, I believe it's somewhere around, 4 looks good. And I'll just scroll this on down a little bit. Let's take a look at terminology. So, this is actually going to be real simple. I just want you to become familiar with, about 8 different words that you're going to hear often, depending on what book you're reading, what other programmer you're talking to, etc. And these words are used to describe the type classes you've just looked at. So we already know that base and derived go hand in hand. Okay? So let me just kind of split these up. So you can see which way we're going, from base over to, from our parent to our child, if you will. Oh, what do you know? The next one. You may hear parent, child. You may hear ascendant. And of course with that would be, oops, let me fix that T, would be descendant. That's actually pretty popular in several of the books out there. You know, this class is a descendant of. You know, that's just, again, just common language. And then another big one. We have superclass. And you're going to hear this one even more than superclass, which would be subclass. Okay, so superclass and subclass. Just keep these things in mind. Basically, all you're referring to is a base class and a derived class. That's it. It's just that simple. It's just you may hear it referred to as, hey, the parent class needs to have this corrected. Or I'm going to subclass this class and add the following functionality. Or this is a descendant class of that particular class. So you may hear all of these words thrown around. They all mean the same thing, okay? Basically, base, derived. Okay? So that's your terminology lesson for today. Now what I'd like to move into is something that's extremely important, and this is member accessibility. And with member accessibility, what we're looking at are the access modifiers. So I'll jot them down here. We'll talk about them for just a second, but then what we're going to do is go back to that example that I just wrote out and Logan coded and start playing with some of these access modifiers. So what do we have? Well, public. We've got protected. We've got internal. We've got private. And you can do, internal protected if we want to start adding these guys together. But let's just focus on just these right here, okay? Now, public. Public means it's accessible from everywhere. And in the code that we've been writing so far, our extended classes, the final class, we're able to easily access everything back up in the base class because everything in the base class was public. But external to those two class definitions, everything out there was able to access it too. So Spider was able to gain access to the name directly, to the IQ directly. We may not want that. That's not really good stuff. So public may not be exactly what we're looking for. Protected, though, gives us the feature we may be looking for. I want to be able to have a derived class access members of a base class. But external to these two classes, I don't want to be able to see anything that was in the base class marked as protected. I don't want to be able to see it from outside. So it's as if I made it private, but I said, everybody who derives from me, you guys are like buddies, so you can see it. But outside, can't see it. Okay? Internal, we know the deal with internal. Internal's like Mr. Public, except for he's just a little bit more protective in that he doesn't let any external assemblies access him. Okay? Private. Think very carefully when using private when we start talking about class members that need to be inherited. The moment you mark a class member as private, what you have just done is locked that particular member to that class. A derived class will not have access to it. Okay? That's very important to understand. So you've got to be careful with private, because you may be thinking to yourself, I want to make sure that name and IQ can't be set back in main or somewhere else in code. So let's just mark it as private. Well, you then just may have broke any classes that extend the game item class, because they can't access the IQ and the name either. So let's go ahead and pull up the example that we were just working with a second ago and take a look at this. All right, in this particular case, like I said, we have marked everything as, ooh, isn't that nice? Giant no-no warning. I'm going to leave that because for a moment that'll really work out nice because you guys can see where my mouse is at. Right now, everything's marked as public, which means since our position and our name are both public, down here in enemy, they have access to them. And we proved that, we proved that down here in our show info method, where we just access name like it was no big deal because name's public. But the problem could come from somebody outside. He's outside the family, and he can touch that particular member. You may not want that functionality. So in that particular case, how would you go about locking the particular member such that it is accessible by all extensions of the class, but you cannot access it externally? We would mark it as protected. So let me go ahead and bring my layer control back up and shift this over so that I can do a little writing. So what we would want to do in this particular case is I would want to take position and name and make them protected. Interesting thing is, though, we just broke our program. Because right now, what's happening with name? How does name get information? Name gets information from up here, where we are accessing name through a reference. We're no longer allowed to do that because as far as it's concerned, the reference is concerned, name doesn't exist no more. It's private. It doesn't have any sort of access to it. Okay? Now, inside of enemy, we're not going to get any problems whatsoever from this guy because this method still sees name as if it was public. He still has access to it. Let's demonstrate this, Logan. Back over in the program that you wrote, let's just go ahead and change the two members inside of game item to protected.
Okay, so here we go with the game item class. We have our public vector2 position and our public string name. If we simply change these to protected, and both of them, so name protected as well. Alright, so we have now changed the game item members to protected.
Okay, so now if Logan builds, we're looking at a problem. Go ahead and build. There is a problem, one particular problem, which is saying that the name is inaccessible due to its protection level. Let's find where the problem is. It's not inside either of the classes, game item or enemy. It's all the way back up here in main, right here. We can't get to it this way. Now, remember when I talked about the difference between protected and private, where if we were to mark one of these as private, then it is more or less only accessible inside game item, and outside of game item, you no longer have any access to it all. Even if you have derived from game item, you still don't have access to it. So if Logan changes protected for name to private and builds again, instead of seeing only one error, we're going to actually have two. Because back up in main we can't access it, and down here inside the show info method we cannot access it. So Logan, be so kind, if you'd be so kind as to go ahead and change protected for the name member to private. And that's good. Let's go ahead and build real quick. Check it out. Like I said, we now have two errors. Notice how name is underlined right there. Once again, Name is inaccessible due to its protection level, and the other one, same thing. Name is inaccessible due to its protection level. So you see the underlining? Can't get to it. Can't get to it. The only person that can get to it are members inside of game item. So that's very important. That's decisions that you have to make when you begin designing your classes. You have to ask yourself, all right, this member that I'm about to create, does he need to be accessed by the outside world? Does he need to be able to be accessed by any classes that derive from me? These are very important questions, because if the answer is no, the outside world does not need to see him, and no, any derived classes do not need to see him because this guy's job is something very specific, then you'd want to mark it as private. And that way you've protected it from the outside world and any extended classes. But if you need your derived classes to have access to it, then you'd want to mark it as protected if you want to keep it away from the outside world. Okay? But once again, allow derived classes to access it. Logan, anything you want to add to the access modifiers?
Well, inheritance really adds another dimension to the idea of accessibility and access modifiers. Before we got into inheritance, we looked at accessibility as inside of a class and from the outside of a class. So we have two ways we can access things, from the inside and from the outside. Inheritance adds a whole other dimension. It adds another way to access from as a derived or as a child.
Exactly.
So it's a third new way of accessing something, and that's where we introduce the protected access modifier, so that we can have precise control on how something is accessed. Private means inside the class only. Protected means inside of this class or inside of derived classes, so we kind of open up that member to anything that's derived, but still keep it private from the outside world, so we can't peer in if we're not of that type, of that class.
Exactly.
And finally, we still have public, which is allow everything to see it, things outside of it, and including things that derive from it.
Okay.
And I guess the only one last thing to point out is that, just once again, the terminology for internal can seem tricky, because the connotation of internal is that, okay, make this less accessible. But in this case, where we have private, if we make, or even better, let's say protected. If we make protected, let me pick on name. So let's make name internal. Even though internal seems to make some, or it might make it seem less accessible, it actually makes it more accessible, because now if we build, we've cleared everything up.
That's right.
Because we have to remember that internal is assembly-wide, whereas protected, private, and public are class-wide.
That's right.
So again, even though internal in this case actually made name a lot more visible, because we said, all right, I'll take this entire assembly, make it internal to the entire assembly, which means outside of the class, descending from the class, we're all inside the assembly.
Exactly. Very cool. Okay, so that is a look at, let's go ahead and switch back over here. Member accessibility, and you can see how important it is, because it simply controls when you're in. Let's go ahead and take a look at this once again. You're inside this instance, and inside the instance you have all of these other instances, right? So this could be like game item, pawn, and then enemy. Depending on, what's accessible, you may or may not be able to gain access to these guys. And that gives the illusion of you inherited it or you did not inherit it.
Right, and that goes back to that idea of flattening all of these instances down into the actual reference instance.
Right.
And that is, the flattening doesn't necessarily give you everything. Access modifiers allow you to control what ends up being seen by descendant classes.
Precisely.
So when everything is, if you want to call it flattened into that final instance, you're only going to see things that were public or protected or private and in the very last, or in the current derived instance. The very bottom or last one.
And as a matter of fact, let's go back to that original description I gave you guys for what is inheritance. Inheritance is a method of creating a class that is based off of an existing class. We've now seen that. Through inheritance, this new class, which is called the derived class, inherits all of the accessible class members of the original class, which is called the base class. So there it is, all of the accessible class members. So if they're not accessible because they've been marked as private, then it doesn't appear that we get them, because we don't have access to them. Very, very important to make sure you understand that. All right, very cool. So let's go ahead and bring this back up and jump back over here to this, our first slide, for just a moment. And let's go ahead and, I always forget to do that. Let's go ahead and jump back up here real quick. So we've looked at what inheritance is. We've looked at why to use it. We've looked at syntax. We have looked at terminology. And we've also looked at member accessibility. Now the little example that we just had a second ago gets even more interesting when I tell you that we may not inherit the member, but that doesn't mean we can't set the member. What? Actually, you've already seen this. Okay? When we introduced constructors, we showed you that we could have private members inside a class and that we could set those by passing information to the constructor. We also saw that every single class has a constructor. If you do not explicitly define a constructor, one is put there for you by the compiler, and it's called the default constructor. Now, we have default constructors in all of the examples that we've created so far. Now, what happens with constructors when we go in there and start explicitly creating them? Or better yet, even if we don't, what happens with constructors when you're dealing with a hierarchy of classes? This is very important. And this brings us to our next discussion, which is constructor execution and parameters, because this is very interesting how this works. So what I'd like to do is, first of all, come up here and create a new slide. Whoa, all right, we're doing good on writing this time around, Logan. All right, and let's hide this lower guy. And let's go ahead and jot down constructor execution. All right, so with constructor execution, oh boy, this is where things are going to get fun. Let me go ahead and write out a very simple application using game item and all that again. I'll change it up a little bit so that everybody has constructors. I'm going to show you what happens. We're going to trace through it, and then I'm going to have Logan go over there and create a new console app and demonstrate it. Basically, when you have a constructor for a derived class, it gets called, right? The first thing it's going to do is initialize its members. Then it is going to call the base class's constructor. All right, so now we're up to the base class. What does it do? It initializes its member. And then if it is a derived class, it'll call on its base class. And this chaining just simply continues until we finally reach the true base class. So now let's say we're in the highest level, truest base class. We're at the root. So now at this point, and of course I'm not counting object, but so we're at game item, or actor, okay? So let's say we're an actor. So now what you're going to do is everything's initialized. So now you actually execute the code within the constructor if there is anything there. When that's done, we then go to the class that extends actor. We then execute that constructor code. We then go to the one that extends it. Execute that constructor code until we finally get back all the way down to the class that you instantiated in the beginning. Okay, so let me draw this out and demonstrate it, and we'll do simple write lines and prove to you that this is indeed working. So let's start out with some simple stuff. What if I had a public? I don't know why I'm doing public. That's funny. So let's go ahead and back that up. This is me getting carried away. Let's do a class called game item. And inside game item, let's go ahead and explicitly create a constructor, just a default constructor. We're not worried about parameters at the moment. So we're going to have a public, and it has to be the same name, game item, no return type, as we all now know. And inside here, look at what I'm going to have you do, is we'll write out something like game item instanced. I'll say create it. That'll work. So we'll know when this constructor gets hit because it's going to write something out to our console. All right, and we'll go ahead and end that right there for game item. Now let's create another class. Let's do pawn, because now we're going to get more specific. And pawn is going to be derived from a game item. Okay, simple enough. And inside here, let's go ahead and create our constructor, public, and then pawn, same name, open, close. Now, this is where things get fun. And we took a look at this way back in the constructors video that just happened very recently. And in that, we said that we had some initializers that we can use with constructors. We have an initializer this and initializer base. Let's go ahead and explicitly put that in there. Okay? We don't have to because we're not passing any parameters. But I want to actually put it there.
Just to get an idea, just to get a feel for what it would be.
Just to get a feel. That's right. Because I've already shown you an implicit way. It's right there in front of you. I can do this. I can call upon base right there.
Yeah, implicit works very well there because that's exactly that. Even without putting that there, the call to base, that is implied. That really actually happens.
It really does. Absolutely. The compiler takes care of it for us. It calls the object in which we inherit from. Object. Okay? So just so anybody doesn't get me, what object are you talking about? The object. So when we basically call upon the constructor for object. Okay? So, but again, so back down here for our initializer. So do a call to base. And in here, login, same thing. We'll just simply write out something like pawn created. All right, nice. Now, let's go ahead from there, close all this off, and jump down to our final class. Finally, we created an enemy, which is going to be derived from pawn. So that we've created a nice hierarchy here. And then inside here, let's go ahead and define a public constructor. And again, enemy, no return type. And even though we don't have to do this because it's all default constructors, let's go ahead and come in here, explicitly put a call to base. Because we're going to start dealing with parameters in just a second. And we'll close everything off. And then let's put some writing inside of here. Let's go ahead and write out same type thing. Enemy created. All right. And this is really going to work quite nice because, as I said a few minutes ago, that when you instantiate a derived class, you get an instance of, well, everybody that's involved in that hierarchy. So you're going to actually get to see it here because the console is going to show you that, oh, a game item was created, oh, a pawn was created, oh, an enemy was created. Just keep in mind, all of this is grouped together and the entire thing is considered the instance, okay? So now, what is actually going to take place here if we were to do something along the lines of enemy, and we'll just call it enemy, equals a new, and let's do a call to the public constructor, enemy. Open, close, terminate. Da-na-na, da-na-na-na-na-na. So right here we are making a call to a public constructor to have it instantiate a class. But when we get to the public constructor, well, first thing, as we know, to be fair here, all of our members are initialized. Okay, so all of our instance members for this is going to be initialized. Now, base. Da-na-na. We must do the initialization before we can do the constructor. Dun 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 dun. So here we are back up here. So now inside a pawn, once again, all of our members are initialized, and then we have to, once again, do the initializer first before we can execute the code inside of this constructor. Dun 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 dun. Sound effects are free tonight. Dun dun dun, and brought to you by me. And so here we are, all the way back here. Once again, inside a game item, first thing that happens is that we're going to have all of our members initialized. And then technically, there is a call even further up because it, again, is implied. Dun 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 dun. for object. So we go back up there, object takes care of itself. All right, now let's just pretend that we start here for real. Everything has been taken care of inside of game item. So our very first constructor to truly run, again, I'm just not taking object into account. We all know that object takes place.
And in this example, there's no object created console write line back in object either. So for our visual example, we'll see this as the first write line.
Exactly. So now this constructor is executed, and our first piece of information is written out to the console. So game item created. All right, very good. Now, once that is done, now we return back to who called us. Okay? Well, everything's instanced in here, and we took care, or excuse me, everything's initialized in here, and we took care of the base. So now we get to actually do the constructor's body, the code within the constructor. So the next thing that is going to write out is going to be pawn created. All right, once the code is finished from within the constructor pawn, what happens? We go all the way back down to here. Once again, everything has been initialized. Base has already been called upon, so now we finally get to execute the code inside of the enemy's constructor. So we will see enemy created.
So we'll actually see that written out as the third line.
That's right. So that is, as Logan just said, the third thing. Okay?
No, actually the created line, but I mean, close enough. It's between the two.
Yeah, but I'm pointing to the constructor. That's what I mean. So this is what we're going to see, though. We're going to see game item created as the very first thing, then pawn created, and then enemy created. Constructor chaining, ladies and gentlemen. That's what's going on right here. So we are walking through a chain of linked constructors, if you will. So Logan, if we could, let's set this up over inside of Visual Studio and show them the console saying exactly what we've shown here.
Okay. Let me begin with a new project.
Okay.
And in that project, we can begin defining some of these classes. Let's start with class game item. And game item is going to have a public constructor, so a public game item. And its job is going to simply be to write out on the console. So I'll have a console write line. And that write line is simply going to say game item created.
Okay. Beautiful.
Alright, now let's take a look at pawn. This is going to be class pawn. It extends game item. And it's going to have a public constructor. So it will be public pawn. And
it is going. Let's go ahead and call, because we can show afterwards that we can put it in and take it out. And it doesn't break anything. So let's go ahead and put it in.
But so for this one, we're going to put
explicit call to the base.
So explicit base, and it's a call to base, so we have to put the parentheses around it. And
it does that. I prefer to have it up on the same line like that. It looks better. That's just me.
I can see, like, maybe if you had a million parameters, eventually you'd run out of space. But for a simple example, it just looks more streamlined to have it all in one line.
Agreed.
All right, finally, we have a enemy class. So class enemy derives from pawn. And it too has a public constructor. So I'll have public enemy. And it is once again going to call upon base explicitly, like so. And I suppose I should put the braces in first and then extend, then we wouldn't drop them the line, but oh well.
That's okay. All right, so let's go ahead and do a console.
Oh yeah, I was jumping ahead from some of these. As a matter of fact,
copy and paste.
Since we've defined the classes, now I'm going to get lazy, copy our write line, and paste it into both.
Lazy, that's just being smart. All right, let's go and change the text.
Where this is a pawn created and this is an enemy created.
All right, now let's go ahead and jump all the way back up to the top and create a variable of type enemy.
All right, so type enemy, we'll simply call this enemy, and it will be equal to a new enemy.
All right. And now let's go and just tell it to read line.
All right, put in our read line, and I believe that's it.
So, as you've seen here, this is basically exactly what's going on back over in the whiteboard. We haven't done anything other than instantiate enemy. But in instantiating enemy, enemy is derived from pawn, and pawn is derived from game item. They all have public constructors. As we know from our lesson in constructors, that all classes always have a public constructor. If you don't define it, the compiler puts it there. Now, in this particular case, we have explicitly called upon each of the basis constructors to run in the initialization part, or the initializer part of the constructor definition. So, we should see the very first thing is game item created, then pawn created, and then finally enemy created. Let's go ahead and build the solution, make sure all builds, and let's execute. Check it out. Game item created, pawn created, enemy created. So game item, pawn, enemy. Go ahead and close that.
Okay, and there we go.
And back over here, game item, pawn, enemy. So it worked out exactly like we described. Very cool, very handy. Now let's go ahead and jump back over to the code real quick, Logan, and let's take base out just to demonstrate that since it's a default constructor for each of these guys, meaning it's parameterless, we do not have to explicitly go in there and tell it to call the constructor. It will just happen implicitly.
So we could delete the call to the base constructor off of the pawn. If we build, everything is still successful. We can run and everything runs the same. We could do the same thing for enemy. We could remove the call to the base constructor, build and run, and everything continues to run.
Everything is exactly
because
the same.
Again, the call to base in that manner was exactly the same as the implicit constructor, or the implicit call. As a matter of fact, we could, like you were talking about with object, we could actually go all the way back to game item. Even though we have an explicitly extended object, technically that's what's happening. So we could do something like
a call to base there.
Call to base, and that is still completely fine.
Absolutely. And you saw, yeah, compiled, ran, no problem, because object does exist, ladies and gentlemen. Okay? Very, very nice. All right, so now that's basic constructor chaining. That's all fine and dandy. What happens the moment you have to start passing arguments to constructors, meaning that constructor is expecting parameter input? All right? Let's go ahead and jump back over to the whiteboard real quick, because it's going to happen. All right, there it's definitely going to happen. So how do you go about taking care of this particular situation? Let's see. What if? Well, game item, we've been saying that game item is going to contain name, right? I mean, throughout a lot of our examples, that's where we've been sticking the name field. So let's go ahead and say that we have a private. Ooh, now I'm getting tricky. I'm locking this out from everybody else. I'm just maintaining it only inside the instance of game item. So and there goes back to me saying maintaining its own thing. So private, like I said earlier. All right, back on track. Private string name. So now we need to set this somehow. So the way that we set this, go ahead and just make some room here, is in the constructor we take in a parameter, a string, and I'll do name. Okay, I'll fix my little arrow back. There we go. Now, inside the constructor, now I can do this dot name equals name. Terminate. I'm just trying to squeeze all this in there. I can clean this up just a tad for you guys. There we go. That looks a bit better. Okay, so this dot name equals name. But adding this in and not changing anything else breaks it. Because even though we're instantiating enemy, game item is going to be instanced. Since it's going to be instanced, that means the constructor will execute. Since the constructor now takes parameters, let me say it a different way. Since the constructor has been explicitly defined, the compiler will not put a default constructor there. Since the constructor takes parameters, it better have parameters sent to it or it will explode. Does that make sense? So there's a whole chain reaction that just took place because we put parameters in. Let's demonstrate, Logan, by changing just that back over in Visual Studio.
As a matter of fact, let me simplify everything so that let's for a moment take all the explicit chaining out. So we simply have a series of classes, all perfectly legit and actually a very common practice if all of these were simple default constructors.
Right.
Now let's change.
Yeah,
so
let's
going
go
to game item.
Let's go and give it a public, or a private, yeah.
So a private
string
name. And then let's change our constructor to take in a string name. And then let's use that inside the constructor to set this dot name to that passed in name. All right. So
now,
all that looks all good. We've seen this in the constructors video. We saw exactly how we can take in a parameter and use it. So everything in this case seems like it should work.
Seems. But now here comes the explosion. Go ahead and build. Kaplow! No overload method. Game item takes 0 parameters. It's complaining about pawn right here, and here's why it's complaining. Because pawn is implicitly calling a constructor with no parameters. But since we have explicitly defined a constructor, the compiler did not put that parameterless constructor in, which means it doesn't exist, which means this guy's calling a constructor that does not exist, so we can't do that, which means pawn this constructor must make use of initializer now, and with that, send information. So if I was to come back over here to the whiteboard to make this work, let me just clean this up just a little bit. I would need to do something like, I'm going to do something, of course, that is a big no-no, but I'm going to do something like base and send Bob to it.
And from then on, Bob is the default
Bob
name.
is always the default name of a game item. But this will fix it because I am now sending one string argument. Up here we have one string parameter. Let's go ahead and jump back over there, Logan, and put Bob in just to show them.
All right, if we were to take this constructor, explicitly chain it to base, but now base, the only constructor for base, is the one that takes in a string parameter, which if we wanted to satisfy that, we could feed it Bob. That would indeed work for the base constructor, so if we were to build, all of our errors go away, and if we run, everything runs.
Game item, pawn, and then finally enemy. So there you go. But of course, this isn't practical at all, okay? It's almost like a magic number, but now we can call it magic text. We're just throwing text in there right as the actual argument that's being sent. We don't want to do that. When we instantiate the actual enemy, at that point we'd want to tell the enemy what its name's going to be. But let's take it a step further. I'm going to come back over here to the whiteboard real quick and see if I can just add a little bit more scribble in. What if we also wanted to have the pawn have a health? So we could do a protected integer health.
Because like we had defined before in a lot of our other examples, pawn was the thing that introduced health.
That's right. So here we've put health inside of pawn, but now I need to gain access to it. So I'm going to start changing my code up just a little bit. So here's what's going to happen here. Actually, I'll rewrite this just so that I can tighten everything up. So public constructor pawn needs to pull in an int health. And then he needs to call on the base and send something string related to it. Okay. Now inside of the actual pawn constructor, now we can say this dot health equals health. Terminate. Once again, we broke everything because now pawn must receive information from, well, whoever called upon it. So all the way back down here, who's our caller? The enemy constructor calls base. So the enemy constructor, we're going to have to send some information inside of base. So in here, I could say, send 100. And then that fixes it. 100 gets put up into health, And Bob is going to end up getting put up into name. I ran out of room, so I just used a question mark. But that's Bob.
Right.
Okay. That's all fine and dandy. Let's go ahead and set this up real quick.
Okay, just so that we have different things for our constructors, but yet satisfy those requirements.
So still protect it.
And if I could spell protected. There we go. This will be a protected int for health. All right.
And now let's go ahead and take that in.
So the parameter will be int health. Then in the constructor body, we can set this dot health to be equal to whatever value was in health. All right.
Okay. Now let's go ahead and we'll try to build, and everybody will see that, boom, we have another one of those pawn takes 0 parameters, so no overloads. It's because enemy is calling upon the pawn's constructor implicitly, and it's calling a default constructor, which pawn no longer has. So go ahead and put an initializer in there. Let's do base and send it 100. Now when Logan comes in here and builds, all errors went away, and go ahead and run it. And we see the same exact result that we have been seeing. All right, beautiful. Now, to kind of put the whole thing together, because we've just been slowly piecing this together, let's go ahead and change it so that, and I'll just not go back over the whiteboard because that's getting so messy over there. Let's just keep it in here. I think you guys can follow. I want to be able to instantiate enemy and give enemy a name and a health amount. So then what happens is we're going to take, let's go ahead and take that in. So inside of enemy, we're going to take in a name.
So string name.
And we're going to take in an int health.
And an int health. There we go.
Now check this out. Now we need to make sure these guys are going to get passed up here, because both of these need to go up the chain, because we're using both of them.
Right,
so,
because name isn't actually used in pawn. It's used all the way back in game item.
That's
but
right.
we still need to know about it when we call game item.
So let's go ahead and put string name inside of pawn. Now the parameter list right here, the signature could have been different. We could have taken in even more parameters that could have just been used inside of enemy.
For example, IQ.
Like IQ. Yeah, that's very, very good idea. Put it in there. I like it. That's brilliant, Logan.
All right, let's make this a private int called IQ.
All right, and now let's go ahead and take IQ in after health.
All right, so we'll take in an int for IQ, and then let's follow that up with an initialization down here so we can say this dot IQ equals IQ, just to finish it off.
Yep, I love it. Okay, so signature here is different than the signature here. We've got string int, and up here we've got string int. But here's what's important. The signatures must match with the initializer, okay, not the actual constructor. So right here, to pass name and health up, all Logan needs to do is treat them as just regular arguments. So name, comma, health.
All right, so looking back above, we have name. And even there, as bringing IntelliSense back into it, we can see that we're calling, when we call base, we're actually calling the pawn's public constructor. That's what base is in this sense. And what does that take in? It takes in a string name and an int health. That's exactly what we have to specify. Now, instead of specifying hard-coded values, the nice thing there is even in the base, or as we call base, we already have our parameters available to us. So not just in the body, but as we actually call the base constructor, we can use parameters from our current constructor.
That's right.
So we can actually feed name directly over into the base constructor. We can do that with any parameter. So we could feed it name and health. That way we alleviate ourselves from having to hard code anything. We can just take that in our most recent constructor and feed those parameters back up the chain.
Now, name and health is going to be sent over here into this name and health. Now all we need to do is take this name and pass it right on up to game item.
So we can just plug name in, and I think that's it. If we build now,
we're going to have an error because now we have a different problem.
We've actually been using enemies. I see.
That's right. So down here, no problems, no problems, no problems. Let's go back to the main method. When we instantiated the enemy class, we called upon a default constructor. Default meaning there's no parameters in this constructor. That's why there's no overloaded method for enemy. So what we need to do is make sure that our signatures match here. Well, what does enemy take? Enemy requires us to send a string, an int, and an int. Okay? So we need to put a string, an int, and an int in there. So the string's going to be the name. So let's go ahead and call this guy Bob.
All right, so feed it Bob.
And then let's go ahead and send it our, the next one's going to be health. Let's go ahead and send it 100. Yeah. And then an IQ 150. Bob's pretty slick. Okay, so there we go. Now if Logan builds, our signatures match. We get a build successful. And when Logan executes, boom, everything shows fine. Now, just to wrap this up real quick, what I'd like for you to do, Logan, is go into the game item public constructor and do one more console write line and say name equals.
All right, so we'll write out name, which I'm spelling with a health for some reason. So name equals, and then we'll actually show the current name. So we'll just put in name. Or to follow better practice, we could even do this on name. I don't know. Either way, I'll just leave a name.
All right, let's okay. And then, all right, now let's go ahead and drop down. Let's do the same thing. Yeah, just copy and paste down there inside of pawn, and let's print out the health. I just want to show that the data is getting properly deposited on its way through the chain as it works its way up. And then finally, IQ. Fantastic. So let's go ahead and run it. And check it out. We have game item, and all the way back up, while still in the public constructor for game item, name is equal to Bob. Then we drop back down to pawn, and we execute its public constructor. The pawn is created, and health is set to 100. Then finally, we drop all the way down to the final derived class, enemy, and the enemy constructor runs with enemy created, and the IQ is set to 150, so that we can see all of our data was properly sent up the chain to the appropriate constructors and utilized properly. Anything you want to add to that, Logan?
No, I think that I think that works pretty well.
Okay. So
there is one thing I want to show, but it's actually separate from this. This shows exactly how we can keep changing what parameters we take in and then making sure that we satisfy the call to base with whatever it was expecting.
Okay.
I've got a completely another avenue I want to show for a problem that can arise. And this actually involves wiping most of this out. Actually, it involves wiping out the game item and the pawn.
Okay.
Let me pretend that we're going to start over completely. As a matter of fact, wipe everything out. I'll just get over to pawn, because that'll show enough. And I'll comment out this line. We'll recreate it here in a second. All right, starting over. Let's say back to creating game item. So we can happily make a class called game item. Only this time, we know ahead of time that for whatever reason we want a name. So I can throw down a string name. We also know that we want to set the name from the constructor, just like we had done in the last example. So in our public constructor, so a public game item, we'll take in a parameter for string name. And inside of that constructor, let's set up our name. So we'll do this dot name is equal to name. And all of that makes sense. That's something we'd seen way back in the constructor video. And I can build, and everything is just fine contained. So that's great. We've got a game item. We could use the game item. But instead, we want to make a pawn.
Okay.
So we've been working. Let's say we've been working on game item. We work somewhere else for a while, and later come back and just jump in and say, all right, time for a pawn. So this will be class pawn. It extends game item. And let's say that's good enough for now. It's kind of like the prop. We know we need one. Maybe we'll add some members, but we leave it at that. We just simply extend game item. And this has worked in the past. Mm-hmm. We would expect it to work now. But if we build, there's a problem. And a problem that's not immediately apparent. If we look at this error, we see that pawn is actually highlighted, class pawn, but we get the message, no overload method for game item takes 0 arguments. Yet it's highlighting pawn. And unless you're really thinking about constructors very closely, that just doesn't make sense. Mm-hmm. That's not an error. A pawn doesn't take in 0 arguments. Obviously, we haven't made it. But to understand what's going on, we have to go back to what we had just seen with the base constructor chaining. So what has actually happened here is since we specified no default constructor, a implicit default constructor was added by the compiler. This implicit default constructor has an implicit call to base.
That's right.
That implicit call to base has no parameters. So what the compiler has in essence done for us is this. There's basically a public pawn that makes a call to base in this manner. And let me block it in, just pretending that everything was finished. So it did this, which on its own, in the sense of pawn, is all correct, until we get here. So let's try to build again and see where the error ends up. Okay, this is making more sense. No overloaded method for game item takes in 0 arguments. So this call, there we can see right there, game item takes in a string name. That's what we actually have to do to fix this. So it could be something as simple as a blank string or Bob. Again, this is the less elegant solution, so what we'd actually want to do is something like, to properly fix this, let's take in a string name for pawn, pass name along to base. And there, even though we're not worrying about name or storing it here, we can build a now everything has been satisfied.
Exactly.
As a matter of fact, what I would probably do if I was really intending to have no code inside of here is put the brackets to the side, because obviously that's just fine. Now we have everything on one line, and we have our requirements for a game item satisfied. So when we create a pawn, we have to specify a name, which is fine, because a pawn is a game item, and game items have names. So we could do game item equals, or excuse me, pawn, just to show using a pawn. So pawn P equals new pawn. We specify Bob out here where we would like to. Everything builds and everything is happy. So once again, just pointing out that if you start setting up a constructor that requires parameters, and then later you go and subclass that class, or you derive from that class, you have to take into account what its constructor is expecting. If there was no default constructor, you're going to have to add a constructor to pawn just so that you can satisfy the requirements of the base constructor.
That's right. Very cool. So that's constructor chaining. It's very important to understand what is taking place under the hood here, because the moment you go in there and you start explicitly creating constructors with parameters that are involved in this hierarchy, you can start getting, well, interesting errors that you're going to need to fix. You're going to need to pass those parameters to those particular constructors. Okay, so that is a look at, let's go ahead and move back over here real quick. All of our constructor stuff. Yeah, I think we lit that screen up pretty good. Let's real quick jump back down here. And while you was talking, Logan, you know, I actually decided on the fly I want to add, well, not that this video is not long enough already, but I decided I wanted to add one more thing into our objectives. Check this out. We've never done this before. I just thought this would be kind of cool. Some on-the-fly adding. How about we do this? So casting's still going to be in there.
Now we have mystery step.
Now we have mystery. How about we show them how we can, we were using the word explicit so much. Explicitly access. So explicitly accessing base members. Ooh. I think that'd be a good one to know.
But first, what does that mean?
Exactly. Well, accessing base members that may have been hidden. Ooh, we've seen hidden before because we've introduced them to that new keyword. Well, what happens if we need to gain access to a member that came from a base class that had accessibility? So in other words, we could get to it, but we, for whatever reason, hid it through the creation of a new member with the same name. How can we gain access to it? I'll make this really quick, but I thought this would be really nice to add in, just since we've made this such a detailed lesson so far. So here's what I want to do. Let's come back over here, and we'll turn this off. And we'll jump back up here, add a new layer. Hide that. I think this will just make it an even better lesson. So once again, explicitly accessing base members. I figure if you can do stuff on the fly, I can do stuff on the fly too. It'll make the lesson a lot more fun.
Fair enough.
Okay, so let me go ahead and just neaten this up a little bit. Ooh, look how close that was. Precision. All right. So all right, I'm just going to use some real cheap names to make this happen quick. So let's say I'm going to have a class called A. And class A has a public integer called health. That'll work. And let's go and just initialize it to keep this very simple. It's 15. Now let's say we've got class B being derived from class A. And so inside it, we're going to do a new public int health. And let's set it to something crazy on the other side, 125. And now let's add a method into class B. So let's do a public void show info. And what this is going to do is I want it to write out what is in basically health equals. And for starters, we'll just append to it health. And terminate. All right. So if we were to instantiate this, what's going to happen on the heap? So we'll just pretend I have a giant box. That's our heap. And then inside the box, here we go. I'm just making this real quick since this is a fast add-on. Here is our actual instance. The instance is comprised of two class instances. We've got A and we've got B. Inside of A, it has a health. And health is equal to 15, as it was initialized that way. Inside of B, he has a health. And we made it 125. You may wonder why I'm not drawing the method. We all know that the method is back in the object type in the lookup table. So this is what we actually have at the moment. So when I call upon show info, but the way the code is written right now, health is going to be the new health that is going to be shown. It is going to be this health. Let's go ahead and write this real quick, Logan, and show them.
Right, just show that it does indeed get hidden.
Yep.
So let's once again begin a new project. And inside of this new project, we can make our classes A and B. So we'll begin with Class A. Class A is not going to be spaced that far. It's going to have
a public int health.
Public int health. And just because I'm picky about naming, we'll...
And let's go and initialize it to 15. We're just making this one quick.
Gotcha.
All right, now let's go ahead and do Class B, derives from Class A.
All right, so we'll have a Class B. And, well, excuse me, and Class B also derives from A.
Okay.
Get that in. All right.
And now let's go ahead and do a new, just so that the compiler doesn't give us a warning. It's not required, just get rid of the warning. So new public int health.
So new public int health. So you want to initialize that one too?
Yep, to 125, big number, so we can see the differences. Terminate. All right, now let's go ahead and do a public void show info method.
So we've got public void show info.
All right, and inside here, do a console.writeLine. Health equals
All right,
health equals health. So again, we should be taking a look at, in this particular case, this health is going to be referring to the health within the local scope. It's going to be the new data member health right here. So we're going to see written out 125. So let's go ahead and up here, instantiate Class B.
All right, so we need a variable type B. I'll just call it B.
That works.
I'll say it's equal to a new B.
Okay, and then let's go ahead and do a console dot, or excuse me, B dot show info.
Okay, so there's our show info for B, and then we can do a console read line. And there we go.
So to show them that the inherited 15, the first health, has been hidden because of the new health data member, let's go ahead and run it and show them that they'll see 125. And there is 125. Very good. Go ahead and close that. And then real quick, I'm going to jump back over here to the whiteboard. So another, like what happens if we wanted to directly gain access to this guy? Well, we could use base access.
Because, I mean, looking at it, it's still public. Nothing has changed that.
That's right.
Something public should be accessible in a derived class.
That's right.
So how?
All we got to do is say base dot health. And this really does go back to, remember you guys learned how to use this dot to talk to a particular, data member within that instance, that particular instance. Well, base is an explicit way of saying, all right, go to the base and talk directly to that data member, because data member's been hidden. So this is how we go about gaining access to it. So now what's going to happen is written out to the console is going to be 15, because that's who we're looking at, thanks to the keyword base. All right, so with that, let's go and jump back over and prove it real quick.
So we could jump down and simply change this to base.health.
Base.health. Brilliant. Run it. And look at that. Health now equals 15 instead of 125. All right, let's go ahead and close that. All right. Whew. Very long, lots of stuff. Let's see. We got some more. I actually have a big thing that I wanted to code out real quick. You up for it, Logan?
Sure. Why not?
All right. So what we wanted to do is let's come back over to the whiteboard real quick and just do a few things. And they can always fast forward, right?
Sure.
So the more the merrier, I say. So let's go ahead and hide this. Let's jump all the way back down here. And on this, we've now taken a look at this new objective that was added in on the fly, explicitly accessing base members. So that's really cool stuff. Now we have casting, but right before casting, what I wanted to do was revisit this. So I haven't forgot about this. With this, I wanted us to actually create this program. Why not? We sat out, designed it at the very beginning. Why not put it in there? Where, remember, we have a game item, and with the game item, it had, position, names, models, and textures. And then from there, we started to get more specific with props, with enemies, and with players. So, everybody, pause at this point if you need to, and refresh your thinking about this very simplistic design that we walked through from start to finish at the beginning of this video. Then what I'm going to do is I'm going to have Logan go over and code this whole thing out just to show a representation of this model that we've outlined here on paper, or digitally, yes. Okay, so with that, they can pause, and they're back. All right, Logan, let's go ahead and jump over. We'll make this quick, guys. Let's go ahead and jump over to Visual Studio, and let's do a new app. And let's start out by creating our classes. In fact, let's just skeleton them in. Let's go ahead and do the game item class, because that's our top level.
Okay, so we'll have a class, game item.
Okay, let's go ahead and create the class pawn.
Class pawn, but we know that pawn is going to derive from game item, so we can go ahead and place that in as we're skeletoning.
Okay, very nice. Now let's go ahead and jump down and do a class enemy.
All right, we'll have a class enemy, which derives from pawn.
Okay. And finally, we have our class player.
All right. So the last thing is a class player, which also extends from pawn. All right.
Excellent. Okay.
Now, what about the prop? Want to throw that in at the end?
I thought we had prop.
Oh,
my bad, we don't. That's actually...
Because this is all followed one branch. We started a game item and trickled down.
Yeah, let's put the prop. I want all of it there.
All right, so finally we've also got a class prop, but he descends from game item. There we go.
Excellent. Okay, so now that we have our skeleton in place, let's go ahead and start all the way up at game item. We said that game item needed to have a name, a position, and a... let's go ahead and reference XNA while I'm talking.
Okay, yeah, for position we'll need vector 2. So
a name, a position, and a model, which we'll just skip model at the moment.
So using Microsoft.xna.framework, this gives us vector 2, so when we go to put position into game item, we have it available.
Also, if you start typing model... No, okay, never mind. I'm getting ahead of myself there.
You're like, maybe... Okay,
yeah,
maybe
hang on. We've been talking now for like 2 hours. Let's go ahead. All right, so set things up.
We could, but we shouldn't.
Yeah, first thing, let's go ahead and create the name. So, in this particular case, let's do a protected string name. I want everybody to see how we're going about setting up all of our accessibility. I don't want name accessed outside of this hierarchy of classes. Next thing, let's go ahead and do a... we can go ahead and do a protected vector 2 called position. Okay, now from here let's go ahead and create a constructor. So it's a public constructor that needs to take in the name.
Alright, so we've got some parameters. Name's a string, so we'll take in a parameter of type string. Let's call it name.
Okay. And we can go ahead and take in the vector2 position as well.
Sure. Let's take in a vector2 parameter called position. All right,
and now let's go ahead and initialize this as name and position.
So this.name equals name, and this.position equals position.
All right, that accomplishes what we were looking for back over on the whiteboard. So let us go ahead and drop down to pawn, because prop's done. And prop's just empty, and we're going to leave prop empty. It's just there for us to extend later, or to add functionality to later if we decide to come back and add some sort of functionality into our props. So for pawn, let's go ahead and start out with a protected health.
Okay, so we've got protected. That should be an integer, I would believe. Yeah, protected int health. There we go.
Okay, and let's go ahead and set up a public constructor for it.
So this will be public pawn, and lock it in real quick.
Now this is where things start to get interesting. When we actually instantiate an enemy or a player, I want to be able to give it the name, its position, its IQ if necessary, etc. In this particular case, all we're dealing with at the pawn is going to be health, a name, and a position. So let's go ahead and take in those three things.
Okay. So we can take in a string name, an integer for health, and a vector2 for position.
And now we need to pass the health and the position up to the constructor and game item so that the signatures match, so that we can properly call it.
Right. So we need to do a call to the base constructor where we feed it the name and the position.
Very nice. All right, now let's go ahead and jump down to enemy. Actually, yeah, let's go ahead and set up this.health.
Sure. All right. I was looking through all these. It's like, what do we need? No, we set up the name. We said, okay, yeah, we have health left.
Now you see why I wanted to code this out, because it's actually pretty big. So health equals health, yeah.
There we go.
All right, so now let's jump down to enemy. And inside of enemy, now enemy has IQ and retreat health.
Okay, both of those are integers.
So let's go ahead and set those up.
And this is the final enemy.
And so they'll be private.
So yes, these will be private. So we'll have a private int called IQ and a private int called retreat health.
Sounds good.
All right.
Okay, so now we're going to need to take in some information here. So once again, a public constructor. And this gives a great example of why you'd want to start using the second line for the initializer, as Visual Studio so kindly tries to set up for you. So again, let's go ahead and take in a name.
A string name. We'll take an int for health. And it would probably be a good idea to make these signatures roughly match each of the base ones, so we don't start rearranging orders like taking in health first and then name first. And then
exactly. It keeps things organized. So we're going to do a vector2 position. And let's go ahead and define its IQ and retreat health.
So let's have an int IQ and an int retreat health.
Okay.
All right.
Now do the colon base. Okay, and then base is going to send up name, health, and position, because that is what the pawns constructor is looking for. Now let's go ahead and set this.IQ. Okay, and let's go ahead and set this.retreat health. All right, very nice. All right, finally, let's see, all the way down at player, we can just probably, instead of typing it all out again, if you want to just steal the public enemy constructor, and then we'll just take out the IQ and the retreat health. Or you can type it all again, whichever way you want to do it.
I actually want to steal the one from pawn. I'll add a few things to it, but that one's
a little bit closer.
More simplistic looking.
Yeah, it's just a matter of adding, or I just want it to select and delete. But it's all up to you.
That's fine. Let me grab the... I don't really have a preference one way or the other. We can grab the enemies constructor. Inside of enemy, let's see, we don't need IQ and retreat health. So none of that.
So I just thought that was better than typing
Will
stuff.
this fit on one line? Yeah, so close, but no.
All right, so let's go ahead and inside there.
And calling this enemy isn't so much going to work for a
No,
player.
we got to change the name. I thought you was about to change the class name. Okay, so that's all.
The other way.
Yeah.
No, that wouldn't work.
Okay, so that's all right. And then prop, we're leaving empty, but we're leaving it there so that we can add functionality to it later as opposed to do in game item.
We'll probably need the constructor to satisfy game item.
Absolutely.
And there's actually another example of that error. It's like, well, why can't we do this? Just like we showed in the last example. We have to put in something to satisfy game item's constructor.
Yep. It needs that name and the position.
So we can do a public prop. I forgot what class we're in for a second. Prop, since we're going to need, what does game item need? It needs a name, health, excuse me.
No, it needs a name and a position.
There we go. String name, vector 2 position.
So let's copy that if you wanted to.
Sounds like a
signatures.
So prop will take in those for the express purpose of sending them off to base constructor to game item. So you send over name, send over position, and then I'm just going to throw the brackets up on the same line because, like we said, we don't intend to put code into prop yet. Okay. So if we build, that takes care of that problem.
Notice he just built and everything worked beautifully. All right, so what we need to do is...
Actually, except for player... Okay, excuse me, I was looking at player. I forgot that we hadn't actually defined fields for player. I was like, wait, we're not initializing?
That's right.
We don't have anything to initialize.
That's right. Okay, so now at this point, let's give an update. Let's use some of this somewhere. So maybe with enemy, let's add another method in here. So let's just do a public... we can just call anything you want. Update, show info.
Show info works.
Yeah.
So public void show info.
And inside there, let's write out some information about it. Let's write out its IQ.
Alright, so let's write out beginning with...
Let's just do name, health, and IQ.
Okay.
3 quick things.
So name shall be whatever is held in name. And we can see that name is in fact available to us. Why? Because back in game item it's protected.
That's right.
So there we go, we have name. And now I'm going to start copying things. We need name. Next you wanted health?
Yeah, health and then IQ.
So I'll print out health, and there's health. And finally
which came from pawn. So name came from game item, and health came from pawn, but since it's protected, we have access to it as if it's part of the family.
And then finally, let's do IQ. Copy this line one more time so we can say that the IQ is whatever is in IQ. IQ is directly inside of enemy. Even though it's private, we can use it because we're in enemy.
That's right. All right, so that we have all that in place. So there, we've got something we can see now. Let's go ahead and jump all the way back up to the top and create some things. So how about let's first create, well, an enemy just so that we can see some actual show information take place.
So let's begin with an enemy. And you want to call this enemy or spider? Or...
Just call it enemy.
All right, this is going to be...
Actually, no, back up and call it spider. I'm going to say the word enemy for the next section. All right, so we're going to make a spider. And he is equal to, well, a new enemy. But we have several things we need to send it. So his name is going to be X. We'll stick with that. And let's start out with a health of 75. And now let's go ahead and give it a vector 2 position.
Which is interesting because we can't directly type out a literal vector 2.
Right.
So since we're not showing it anywhere, I'm actually going to use one of the simple ones. If we look at the vector 2 class itself, vector 2 has some convenient things. Aside from some operations, it has a property called 0. So if you want a very convenient vector 2 with 0 on it, you can actually access vector2.0 to fill in a vector 2 with the values 0 and 0.
Okay. Now from there, let's go ahead and send an IQ of maybe 85. And then they need a retreat health. When he gets down to 15, he's going to run. All right.
And that's it.
And that's it. So now with that, let's do a let's do a spider.showInfo to see that all of the classes were instantiated properly and the constructors handled passing all of the parameters on to other constructors properly, so that all the initializers worked right. So let's do a console.readline.
And there is our read line. I'll space that out a little bit.
And now let's go ahead and do a build and then run. And look at that. Name is X, health is 75, and IQ is 85. So we've taken what we had originally started with a very simple concept on the whiteboard with the game item and all that good stuff, and then we simply went through and figured out what was common to everybody and worked our way from there to more specific. And then as we did, we wrote down everything that we found, and then we started diagramming it that way. And then we used that diagram to actually create our code. And then with our code here, everything works great. Now, I'll just leave this as an open challenge for those of you that are new to this, and it's like, wow, this is pretty cool. Play with prop and with player and put in a show info or some sort of method, and then create some game items. You know how to use lists now. Try to make a list of game items. Now, casting is going to become important when you want to do stuff like that, and we're about to talk about that in just a second. But there's a lot of things you can do with just this little example right here to see how you have these different common items shared. Okay, that's the important thing, such that it really does look like a player has inherited all of these things, or that a rock or a tree has a model and a position, etc. Okay, so go ahead and close that window. Now, I do want to point this out. At the moment, everything is going to look a little complicated when it's like you're going to start recreating code again if you want to start doing show updates all over the place and things like that. The next video, we're going to start getting into virtual and override. This is where we're going to start showing you how you can create some very flexible / intelligent methods, okay? Such that methods that get inherited can be extended. The functionality can actually change. It can morph, okay? But we're going to talk about that in the next video. So if you want to, save this little example, watch the next video, then come back to this one and see how you can implement some of the things you learn over there. Here, do you see what I'm getting at, Logan?
Right, because like you were saying, if we go and start adding things like update, like we've got a show info. There's a show info on enemy. If we start wanting to play around with a show info on pawn, then like you said, it's like, well, wait a second, now we're writing show info over and over again. And that's where, go ahead and do that for now in this example.
Yeah, but we could inherit show info from the top, but if we inherit it from the top, show info inside game item doesn't know about, all of these things further down, so we're going to have problems.
Right, so either way, you run into problems either way.
That's
but
right.
Nonetheless, it'd probably be a good idea to play with this a little, add things to these items, and make a few of them, just so you get a feel for what you can and can't do with the structure. That way, when we get into virtual, you can see how some of these problems can be solved.
Exactly. Okay, so with that little bitty example out of the way, let's go ahead and jump back over here to the whiteboard and check this off. So now let me bring up my first slide. And that means, well, there's nothing to actually check off. That means we're on the very last thing, which is casting. Now, this is a very important one, and it's something that we're going to start using really soon in the game Precision in this volume. We will be making use of casting from one object type to another. Okay? So with that, let me go ahead and hide this. Jump all the way up here. Let's add a new class. Or, excuse me, a new class. Boy, we've been going at this for a while now, Logan. Let's go and add a new slide, hide this, and write out casting references. I'll just write casting. Hands getting tired. All right. So there may be times when you're going to need to cast back and forth between related types. Well, what am I talking about when I say related types? Well, think about it. Game item, pawn, enemy. They're all related types, okay? What happens if you happen to have an enemy and you need to call on a method that takes in a pawn? Well, fortunately for us, in that particular case, we just send the enemy. But what happens if we have, all right, here's a good one. What happens if we have this? And I'll just wipe this out in just a second. What happens if we have a giant list of actors? And inside this giant list are references to enemies, to the player, to props. You get the idea. Now what if we need to call upon some update, and inside of update we need to do different things for the player, the enemy, props, or whatever, right? Now we need to be able to find out, is this particular type an actor? Is he actually a player, or is he actually an enemy? Or what if inside of update we call upon another method that takes in an enemy? So some sort of method that is looking to bring in an enemy in, right? Well, we're going to need to cast our actor up to enemy. But can we cast the actor up to enemy? Is the actor a rock? If it's a rock and we try to send the rock over to this method that is expecting to do some work with an enemy, that's going to cause a problem, wouldn't you say, Logan?
It's probably going to cause an exception.
An explosion is what that means. So casting becomes important. You guys have looked at casting. You have seen how you can take a float and cast it over to an int, or casting in all sorts of different directions and different types of information. But we've never really played around with casting objects before, okay? And that's what we're going to be focusing on here. So let me go ahead. Actually, I'm just going to erase this whole thing because that'll be a lot quicker. And let's start this whole thing out by drawing an interesting little picture for you, because I like drawing the pictures. So we've got casting directions. Now, let us say that we have this interesting arrow. And, hey, that guy was bigger. Okay. And now over here, this is towards base. This might seem a little confusing at first. Bear with me. And in this direction, it's going to be towards derive. Now, why am I showing this? Well, we've already seen that we could have a game item that could then be a pawn that could then be an enemy. So what if you happen to be a pawn and you want to cast to a game item, or you want to cast to an enemy? Notice you're moving in a given direction. So here's our object, right? So the question is, are you casting towards the base, or are you casting towards the final derived class? Now, why is this important? This is important because is the cast going to be handled implicit, or can it be handled implicitly, or do you have to explicitly handle the cast? So let's go ahead and jot that down. Implicit casting, explicit casting. Now, what does this mean? Well, first of all, you should already know what it means. If you think back to the casting video that we had, we talked about implicit and explicit casting. With implicit casting, you don't have to do anything. You could just say that the spider is going to be used right here as a game item. And since the spider is an enemy, which direction are we going? We're going back towards the base. So we just say spider as game item, and it all works out great, right? But if we had a game item and we need to go in this direction to an enemy, we can't implicitly do it because we don't know if in the end it truly is an enemy. Okay, does that make sense?
What this boils down to is whenever we deal with objects, we actually work with them using references. We have a variable that is a reference that points at the real actual object.
That's right.
The key here is that reference, being a variable, has a type. Generally, that is of type whatever game object we're using.
That's right.
But we can run into scenarios where the type of that reference is not exactly the same type as the type of the actual object. It is entirely possible and useful to store an enemy inside of a reference that is of type game item.
Well, yeah, just for the simple fact, with our little example a second ago with a player, an enemy, rocks, trees, have a whole list full of all of the things in your game.
Right, with that list you just drawn up as an example, that makes things very convenient because we can look at this list. This is all of our game items. But the key is that we can only look at those as game items. We might want to get to something specific. So we can take a game item out, and we need to have the ability to say, is this actually an enemy? And if so, we'll treat this as an enemy so that we could do enemy things to it.
Right. So, this implicit and explicit, let's take a look at some syntax. This is what you're dealing with. Type, such as game item, enemy, etc. Identifier. Equals. So here we are. Basically, we're creating a new reference variable. A new variable that's going to hold a reference, right? But even that's interesting, which we'll talk about in just a second. So type identifier equals type variable. So the variable casting. Okay, so this guy right here, he's optional. Why is he optional? It depends on which way that you're casting. If it is an implicit cast, we could have just simply said type identifier equals variable, and that works just fine. But if on the other hand, you are going towards a derived class, so if you're a pawn and you happen to be going to an enemy for whatever reason, then you would have to go in there and you would have to explicitly tell the type what it needs to be. Okay? Very, very important. So let's see, I've got a simple example. Do you want to add anything, Logan, to this before I start throwing out some examples?
I'll hold off until a little bit later. There's something I want to point out between value type and reference type, and this being reference type casting.
Okay.
But we need to get to some examples so we can show that.
Okay, so some examples. Oh, boy. Deep breath, and we shall begin. Let's go ahead and start out with a, let's see. Let me think, guys. I'm just deciding on how I want to go about handling this. To make it easier, Logan, I'm going to bring up another sheet. Just in case this ends up becoming lengthy. So how about we start out with another class called game item. And inside of this particular class, we put a public void update, because this is going to be kind of cool. And here we just write out something like game item updated. Just to show it was called. Okay? And now, let's go ahead and create another class. Enemy. That derives from game item. And with this guy, let's do a new, so do a little hiding here, public void, update. So we'll hide out our inherited update method. And in here, do something like enemy updated. Alright, and there we go. Now, we have a scroll bar for the first time ever. It just became handy. So let's come all the way back up here to the top, and let's do the following. We're going to do an enemy called Spider. It's going to be equal to a new enemy. And we'll call upon Spider's update. Because it's public, so we can do that. And it's going to say enemy updated. Now, what I'd like for us to do is to create a game item variable. So game item, and we'll just call it item. And what this is going to be equal to, now I need, and we're not going to do a new game item. Now what I want to do is I want to store my enemy in here. Okay? So I want to treat my enemy like an actual game item type, not an enemy. Alright, well that might sound really confusing if you're just kind of struggling to understand this whole concept here. Just hang tight. Just hang tight. So to do this, I'm going to first explicitly do this. So I can come in here and I can say, so here's a regular cast. So I do game item. Spider. That's using the syntax we just saw a second ago. Think about it. We had type, we had identifier, equals, cast to type, variable. Okay, and spiders are variable. So now with this, if I turn around and say item dot update, what happens? Ooh, this is where stuff starts to get good. The first thing that I want to address is the picture that I had drawn just a second ago. In fact, I want to be able to jump back and forth quickly just to show. Which way did we cast on this line? Up or down? Well, we wanted a game item from Spider. So if we come back over to our graphic, we wanted a game item from Spider. So if we look at the bottom down here, we went from enemy up to game item. Okay? So that means if we go towards the base, an implicit cast can take place. You don't have to explicitly use the casting operator. So in this particular case, this is optional. So that's how this little drawing comes into play, okay? Because we're very aware of everything as we go in this direction. Not always aware when we go in this direction, which we'll see in just a few minutes. All right, so let's turn that off and this back on. So in this particular case, this was optional. This meaning the whole thing. Okay? What's happening in memory? Because first of all, if I run this, what are we going to see? The console is going to show me the following. It's going to show, first it's going to be enemy updated. Then the next update next thing that's going to be shot out is going to be because of items update. So this ran, we had now an enemy called Spider, we called his update, we now created a game item variable, and we put its reference pointing at Spider, and then we called his update. It's going to print out game item updated. Interesting. Very interesting. Let's take a look at memory. So on the heap, what does this look like? Here's our instance on the heap, with this being the game item. And with this being our enemy. He has his own update. I'm not going to worry about drawing out object types and all that. I think everybody gets the idea. He has his own update. He has his own update because he hid the other update with new. So there's two completely unrelated update methods here. That's very important to understand. Now, let's look at the stack. At the very beginning of this video, I said some books kind of get this next thing wrong. And you're about to see what I'm talking about. So the stack's cruising along, dink, dink, dink. It's all nice and happy, and suddenly we created Spider. Spider contains a reference. Let me finish. Let me correct the enemy. There we go. Spider contains a reference to the instance of enemy. But the instance of enemy includes an instance of game item. Here's a brand new way to read this. An instance of enemy includes game item. Okay? So there we go. Here is our true enemy. Spider points to the entire instance. So if we were to look at the true reference is pointing to that. Now, I turned right around and I created another variable of type game item. Item. A lot of books will tell you the following. Well, not a lot, but there have been several. That spider actually points to the end result right there. Okay? And that item, since we have now cast item to a game item, it's going to point to game item. That the reference has now been updated to point to that. This is not true. And you can easily prove this by taking advantage of some of the functionality built into the object class, where we can compare references. Okay? You will find if you do that, in fact, if Logan feels like it in a few minutes, he can even do it for you. But you will find that both spider and item, in all actuality, point to the instance, points to enemy, which is, well, all classes instantiated for the final class that we instantiated. Okay, so everybody that's involved.
As a matter of fact, I want to prove that 2 different ways when we get to it.
Oh, sweet. Look at you go.
Reference equals is one of them.
But notice how I just drew those little dashed lines out? They do apply. In my opinion, they very much apply. But it's some other magic that's happening under the hood. I want you to understand that spider and item point to the instance enemy, but their types point to the instanced type inside. Okay, if you want to look at it that way. So item does indeed point back over here to the game item instance. Now, if you were to look at the reference is to the entire enemy instance.
It's almost like the fact that item points at game item specifically in that list is more so that you're setting the level at which you look at that entire thing.
That is right.
And more so than just one of them. Because if item is looking at everything like a game item, game item's technically an object because everything's an object, you're not going to be lacking any of the object things. You'll see all the object things. So you could draw another imaginary box right above game item. So item is going to be looking at game item. It can't see past game item because it's of type game item. That hasn't precluded anything that came above.
That's right.
So it's more like whenever you cast to something else that is higher up than your ending final type,
everybody below gets eliminated. It looks like it's out of scope.
Right, it goes out of scope. It can't be seen.
That's right, can't be seen.
And that means you've limited your level. You're not looking at game item only. You're looking at game item and everything that came before it. So it's like you've changed your level to game item. Everything else is still there. You've just looked up a few.
Exactly. Now, I can prove what Logan just said. Spider is pointing down here to enemy in regards to the type it's pointing to. And we can see, from this point, everything back above it. And we've seen that over and over and over in the different examples that we have basically worked through in this video right here. So enemy had access to the game item's name and position. Same thing. It can see everything above it in the hierarchy.
If you want to go back to the flattening look at things, if we look at that as an enemy, that means we flatten all the way down to enemy.
That's right.
If we look at something as a game item, it's like we flatten only to game item and then take everything else out of scope.
That's right. But it's not, by doing this, we're not affecting enemy whatsoever.
That's a very key thing to understand because if you remember value type style casting, you would look at the fact that the type we're casting to being optional is a very odd thing, or the fact that you can I thought I was thinking of the wrong thing, but the fact that you can implicitly cast from what we can call a more complex type down to a more simplistic one. Why does that actually work? Because in value type, when we're dealing with data sizes, if you cast from a larger data size down to a smaller one, you're going to deal with data loss. And you will have to explicitly cast. There is no implicit cast.
That's right.
If data loss is involved. Well, there's the key. When you cast from something down to a base, you're not actually losing any of that information.
Nope.
Even though it's going out of scope and you're hiding it, it doesn't go away.
That's right.
If you were to cast back, your information is still there. That's why you can implicitly cast, is because no information is lost.
Exactly. All right, so in this particular case, we've got enemy updated and game item updated. So, Logan, if you want to code this in real quick, then you can even prove that we continue to point to the reference.
All right. So let's begin a new example. Let's start a new project, and there we go. All right.
So let's go ahead and create a game item and an enemy class.
So class game item. Class game item is going to
contain a public void update.
So public void update.
And it is going to do a console.writeLine, game item updated.
All right, writeLine, game item updated. Very good.
All right, now let's go ahead and jump down and create an extended version of game item called enemy.
All right, so enemy extends game item.
And in there, let's do a new public update. In fact, you can copy that whole thing and just add new to it and change the writeLine.
All right, so if we steal the entire update method, of course it's the same name, it's going to hide it, so we'll say that it is going to be the new public void update, and this is going to be enemy, so we can change this to say enemy updated.
All right, very good. Now let's go ahead and go back up to main. And inside of main, let us add some code. First of all, enemy called a spider is equal to a new enemy.
All right, enemy spider equals new enemy.
Okay, and now let's go ahead and call upon the spider's update.
All right, spider update, and there we go.
All right, now let us create a new variable of type game item.
All right, we'll have a game item. Let's make that.
We'll call it item.
Item.
And in it, let's go ahead and explicitly cast.
So on store, then we'll explicitly cast to game item
the spider.
And there we go.
Okay. Now let's call upon the items update.
So item dot update.
And now let's do a console read line.
And console. We'll have our read line.
And let's go ahead and build.
Build, and everything succeeded.
And run. Check that out. Enemy updated, game item updated. That's exactly what I said would happen back over there.
Very nice.
All right, now Logan, it almost looks like, because we've said that game item is instantiated, enemy is instantiated, it almost looks like the reference is changing around, pointing from an enemy that has access to game item to just the game item. Can you prove to me that that reference stays the same?
Indeed, I can, a few ways. The one thing I want to point out, just to point out the
go ahead and take that
cast, if we take out the cast to game item, everything still builds and runs because, again, like we were talking about, which direction are we going? We're going to base. Game item is a base of enemy, so we can implicitly cast in that case. We can directly say that game item is equal to spider. Though even in that case, it kind of looks like item is now a different reference because two different things end up happening.
That's right.
So let's take a look at this. So have we indeed lost information in taking our spider and storing him in a game item? Well, let's add some information so we can test this. Let's go into let's go into enemy. Inside of enemy, let's add a public, just so I can get to this from wherever. Let's add a public int called IQ. And for brevity's sake, let's go ahead and initialize that to maybe 85. Just so we have some piece of information that goes along with enemy, that is part of enemy. And then, to show another piece of information, we could actually go into game item and put a public int health and set that to 100. So we have a piece of information that exists on game item and a piece of information that exists in enemy. So to start off with, the important one we want to look at is IQ, because let's say that after we make our spider and update him, that we take our spider, we set its IQ to 150, so he got smarter for some reason. So now we've actually done something to IQ, and now we cast to item. So let's see here. I'm just thinking for a second on how I want to actually show that. Now let's jump back out and do a console read line, so that after all these things take place, we put a spider into an item, Let's now turn around and go ahead and get our item back out of game item, put it back into an enemy.
Okay.
So let's say later in code, we have an enemy. And this time, let's make an entirely new variable. Now let's call him enemy.
Okay.
We'll say that is equal to item, because we want to follow the chain along. So we've put spider into an item. Now we want to take item and put that back into an enemy. Now, if we try to do this outright, and we try to build, that is an error. We cannot necessarily take an item over to an enemy.
Think about which direction we're trying to cast. We're now trying to go from high level to low level, because this is base, this is derived, and going in that direction, it has to be an explicit cast.
And why is this dangerous? Well, we could store things that are not enemies instead of game items. We could make something that actually is just a game item and place that in item.
Or what if we had a prop or a player? Right?
Exactly. All those would also be a game item. So if we put a rock into item, which would be perfectly legal, we could do that.
So we don't know. So in this case, since we're casting in that direction, well, to make sure that everything is, well, valid, we must explicitly cast.
So that means we need to tell it that, yes, we know that this is indeed an enemy, so let's cast this to enemy explicitly and store the result in enemy. And then let's turn around and do something meaningful with enemy, like take console write line and just write out his IQ. So enemy's IQ is, and then add on enemy.iq. Alright, so if we build, that takes care of our error because we're now explicitly casting over. And this is the part that goes back to the test and the proof of the fact that we didn't lose any information by putting the spider into a game item. Because what we're going to do now is we're showing IQ. IQ is set. I didn't actually even have to initialize it, but that's fine. Because we took spider and we set a specific IQ. So we're looking to be able to store the information 150 in IQ. But later we take spider, we take the enemy and put that into an item, and then do things with it as an item. Later we take that item and put it back into an enemy, and now we're looking at IQ. So has IQ survived the trip into and out of a game item? Well, let's run and check. Enemy's IQ is 150.
So its state is exactly how we left it.
So that piece of information survived. Again, this implicit cast was allowed because we did not lose information. We did not lose IQ in going to a game item.
That's right.
Now, things are kind of tricky because remember, getting the game item back out, we had to just know that item was an enemy because we could do interesting things with item. What if we turned around and actually changed this a little bit? What if now in another scenario, for some reason we change the code, an item becomes a real, actual game item?
So throw new in there.
Whoops, yeah, that's... So let's say for some reason now we store a new game item, so not the enemy.
Are you about to get into testing?
Oh, do you want to finish the proof before we get into testing?
Yeah, I want to finish the proof first because that's actually the next part.
Okay, so we don't jump around too much. I got you. All right, we'll put that off for just a second. Let's put spider back in. All right.
Okay.
And, all right,
so that's to prove that game item, or excuse me, just to prove that spider and item both still point, their actual reference is still the overall instance.
Right. We've shown that data can survive, but yes, we can show another thing, and that is the fact that this item, or excuse me, this game item, and this game item spider, I'm calling spider a game item because in essence it is, an enemy is a game item.
Right.
That in this case, because we assign item to the actual spider, that means the item reference and the spider reference really point at the exact same thing. And let's see, how can we do a test? There's two ways we can prove this. I'm going to put off the last way to the very end and just show one way of using item. Well, actually, I'm thinking we can't. The one thing is here, we can't actually access any IQ setting things. We don't have the necessary chaining down here to do it.
Right.
So yeah, okay. This brings me to the final test. Trying to get slick, but yeah. So, what could we do to check and see that these are the same reference? Well, there is some functionality stored in object called reference equals. Its job is to test two objects and to see if they point at the same instance. And we can use that here to prove that this item is this spider. So we can do that with a check. Since it's going to return a boolean, we can do if object.reference equals, and we can do the equals between item and spider. And if that is indeed the case, we could do, let's just do a console write line to give an indication of the fact that they were indeed equal.
And just put in there, both point to same instance.
So both point to same instance.
Because that's what's happening.
So if that is indeed the case, let me finish off the parentheses. So if item and spider are the same instance, we should see this line. If they're not, then obviously it simply won't echo that line out altogether. So let's build and then run. Both point to the same instance.
Very good.
So through the use of reference equals, we can see that even though our item and spider are of two different types, they actually point at the same instance. So that's, again, showing exactly why this IQ specifically survived the trip from item and back out, because item was the actual spider.
Right.
That's why we can get the information back.
Exactly. Now, if we jump back over here real quick, that just reinforces what I was saying about the reference is pointing to the entire thing, the instance, the whole thing. Okay, within the instance is instances of the game item and the enemy. Okay, now based on the type that each of these variables are, so the spider type is enemy. Well, with that being the case, our scope is looking at this instance and all instances that came before it, meaning we can see everything. When we cast it over to a type of game item, we then changed our type now points to that type within the instance, which means we're now pointing here. With that being the case, we can only see from here up. We cannot see down. Okay, that means we don't have those particular abilities available to us. And this is another thing, real quick, Logan, just to, if I wanted to have you do this real quick, I'll jump back over here. Just jump down. Watch this, guys. Throw a public take damage.
So public void take damage.
And you don't even have to put anything in it. Just boom, boom. All right, now go back up above. Scroll back up. And just show where you got item.update, and everybody saw that it had an update. That's because game item had update. But now try item.take damage. There is no take damage. Our scope has now been limited to the type of game item and all classes above it, which is just object, which is why we have equals get hash code get type in there. Okay, but we have lost the ability. I mean, we can see health. Oh, but that's because health is in game item. But we've lost the ability to see things that are below us. Okay, so that's just one more way to re-emphasize this whole thing, because it's really important concept to get here.
The type of the reference controls exactly what you can see.
Exactly. All right. So the next thing is really just one more thing that I want to do, which Logan was getting super excited about and about to show you just a second ago, and that is you've got to use caution when you are casting towards a derived class. So what Logan is showing you right there is we are taking a class, a high-level class, and casting it towards a lower-level class. You better exercise some caution here, because what if item contained a rock? And now you're trying to cast a rock to an enemy which has things like IQ and health and all. That's going to cause the compiler to be very unhappy with you. Or if you're slick enough with the way you code things, it might look like it works just fine, then cause your program to explode and throw an exception. So you've got to be really careful. So back over here, let's move back to this slide real quick. When going in this particular direction, you must exercise caution. And this allows us to introduce two new things to you. We get to show you the is operator and the as operator. Okay? So I'll hand this back over to Logan to demonstrate those two, but by combining these with an if statement, we can then check to see if something is of the right type before we try to do something to it. So there's two different ways we can go about demonstrating this, Logan. Let's go ahead and first focus on the is, because the is has a very unique way of gaining access to members. Okay?
Right. So let's jump over to the console app again, and let's explore exactly why we would want to use is in the first place. How exactly could this explode? Let's show that. Let's take it.
All right, if you don't mind, I'll join you real quick. Let's
Sure.
go all the way down and add a new class. Let's add a player.
Ooh, yeah.
And let's have the player derived from game item as well.
So player derives from game item.
And he doesn't even need anything in it. That's enough for us to make the point.
Sure. So you're saying what would happen if we stored player in item?
Yeah, so let's, if you want to, we can go ahead and instantiate a new player. Now that's something they haven't seen either, if you think about it. But this
directly putting a new player into a game item?
Yep. But that, just letting you guys know, that is completely legal.
Because which direction are we going? Player to base game item can be done implicitly.
That's right. Okay, so now we have game item pointing to a player. Well, better yet, hang on. We have a new player, which means we have an instance of player, game item, and object. But while we're pointing to the entire instance, the scope is at game item because we actually stored the reference in a game item type. Okay? Whew, boy, tricky. All right, now demonstrate.
So this is where the danger part comes in, why you need to use caution when explicitly casting. If you remember, we had to explicitly cast because the system wasn't sure exactly what item was. But we told it that it was okay because it was an enemy. So go ahead and cast and store it in enemy. We've changed things though. Item is now a player. A player isn't really related to enemy in the same sense.
It's not related to enemy at all, technically. It's related to game item, but it's not related to enemy because they branch. The hierarchy branch.
Because looking at it, let's see player. Does player have an IQ? No, it doesn't. So if we casted a player to enemy and tried to access its IQ, there would be an explosion. As a matter of fact, it will explode even before that, which you'll see here in a second. So we know we have a player stored in item. That means that item is no longer equal to, so we won't even see this line. We'll get down here and we'll tell it to take the player and cast it as an enemy. So watch what happens.
Wait. And here it comes.
Waiting.
Yeah, wait for it.
Invalid cast exception. So we were unable to cast the object of type player, console application 1.player, to type enemy. So that was an invalid cast. One cannot do this.
That's right. So again, back to the picture that I had drawn. At this point, keep in mind which direction are we casting. We're casting from a base direction to a derived direction. So we must exercise caution. If you don't exercise caution, this is the kind of problem you can run into. So how can we go about exercising caution, Logan?
Well, this introduces the is operator that you were talking about. We can use is to take an instance and see if it is of type and then feed it whatever type we want to check. So the syntax to this would work like such. We'll put this inside of an if statement because we're going to test the result. And our statement will be if item is enemy, because that's what we're looking for. Mm-hmm. So I'm going to do a check and see if item is enemy. And then I'll block this in like so. So all of our enemy relevant code has now been placed inside of this block. And then we go ahead and perform our cast. So what this should do...
You can even demonstrate, first of all, if you want to put a breakpoint there.
And if we run and break here, now we look at item, and we can already see from the text here that it's a player. So if item is enemy, well, it shouldn't be. So if we step through this, step over, we see we skip these instructions altogether. We skip these statements entirely. Why? Item was a player, not an enemy, which means don't try any of this, which makes it so that now if we were to just run our code straight out,
it runs.
We don't hit the enemy stuff, but we also don't crash the application.
That's right. What's really cool here is we were still able to call upon update, but remember, player inherits from game item. So player inherits game item's update, and we called upon the update. Okay? Just wanted to point that out.
Right. I want to show something else interesting with casting while we're at it here. We've been taking item and putting it into an enemy, though we could have accessed item's IQ directly. For example, let's take this line out altogether. Let's say for the time being we didn't want to hold a reference inside of a variable. How would we actually access the IQ? Let's cast directly in this line here. So we have item.
And we can't go ahead and take IQ out too. Go ahead and do item dot. Just as a reminder, There is no IQ in there. We don't have access to it, even though when Logan changes this in just a second back to an enemy, because up above we're still a player. So we're not going to get in
right,
there.
because, I'll have to change this back to get in entirely. As a matter of fact, let me do that just so I can explain this straight out.
Okay.
Let me change this back to Spider, or even a new enemy.
Yeah.
But by the way, if we change this to Spider, what does that mean? As a matter of fact, I
like you doing it as Spider because I want to show them that 150 that's in there.
Oh, yeah, good point. So if we run now,
So now if he does IQ dot, watch this. So do the dot. Again, or item dot, excuse me. IQ does not show up in there. Very good. But we know, because we're inside this if statement, we're inside the true portion of it, that item is an enemy. So we can actually cast and gain access to all in the same line. So watch this.
As a matter of fact, we had seen the cast before, but that cast involved creating a temporary variable.
Right.
What if for some reason you did not want to have to create a temporary variable?
Because it's a one-time access, like right here.
Well, we could directly cast item to an enemy. Again, an explicit cast. But now, how do we access the enemy-related members inside of item?
You still can't just do dot. No
because
IQ.
Now we run into a kind of order of precedence. What's happening here is that the enemy cast is not running until we actually access a member. So what it's really doing is grabbing a member and trying to cast that member to enemy. Instead, we need to tell it that the cast needs to happen first. And we can change the order of precedence with parentheses. So now, with this cast inside of parentheses, that means before we try anything else, cast item over to an enemy. After we perform that cast, let's see what we have left. If we place a dot after these parentheses, so after the cast is completed, so what we have casted, dot, and there we have IQ. Because we have casted item to an enemy in line, and now we're going to access its IQ.
So now let's build and see what she does.
We build, everything succeeded. We run, the enemy's IQ is 150. So that is indeed the spider's IQ. And that's all very...
So all we've done right here is we said, look, let's just kind of expand the scope back so that we're looking at enemy and below, and then, of course, we can see IQ.
But we are exercising caution in that we first check to make sure that item even is an enemy before we try to use it.
So comment that whole section out real quick, and let's show them as another way that they can do this.
Now, as is another operator that's useful in converting. Now, the way it works is it will allow you to cast... I guess you could say it will allow you to cast in a more safe manner. What will happen is it will allow the cast to occur in any case, and if you were unable to, if the cast was invalid, instead of throwing an exception, it will set the reference to null. Let me write this out and show what happens. And for this one, I am going to want to store a variable reference straight out. It'll make everything make more sense. So I'm going to start a new enemy reference called enemy, and we're going to set that to item. But of course we're going to have to cast, and we're going to cast using or convert using the as operator. So we want to say that enemy is equal to enemy or item as, and we specify the type. So enemy.
So item, of course, is a game item. So we're saying, look, take this game item and treat it as an enemy. And if it can, then, well, it will return that reference back. It'll work properly. If it cannot, because items like, let's say, a player, that would be like, say, treat this player as an enemy. Can't do that. So it'll put a null back in enemy. And now you can turn around and use an if statement to test enemy to see if it contains a null.
Right, because naturally doing something like this, as a matter of fact, I'm going to steal this line back, the console write line. Now if we write out enemy's IQ is, we have the enemy variable, so we say enemy.iq. This is, again, unsafe. Even though now we have a scenario where the conversion won't throw an exception, we have now set up a scenario where enemy could be null. If we try to say null.iq, that will throw an exception.
So let's go ahead and put an if statement in there.
So now we can do an if statement, but what do we need to check? Well, we need to check enemy itself. Because, again, like we were just saying, that if item was not an enemy, and we try to view it as an enemy, we get back a null. So the check now needs to be if enemy is not equal to null.
That means it's equal to something.
Then we'll go ahead and write out the line because, so enemy is not null. That means there is no problem in accessing this enemy.
And we can run it.
And we get enemy's IQ is 150, just as expected.
Beautiful, beautiful, beautiful. All right, Logan, the floor's still yours. If there's anything else you want to add to this, because this is an important one.
Right. Well, just showing that there's options involved when casting, because I mean, in either case, we can define a temporary variable, though in this case, it's more useful because we could say if item as enemy does not equal null, that would be a valid check, but we never stored a reference to enemy, so it was kind of a pointless check.
Right.
We could say item was an enemy, but we couldn't access it. That's why I went ahead and from the beginning stored this result in a variable, so that I can not only check that result, but then turn around and use it. Just more useful that way.
And another thing to point out, just kind of a tip, while this may be really handy, what if you needed to access 15, 20 different members for something? You may not want to have to go in there and handle all of this casting every single time. That's not efficient.
Right, because you're performing a cast over and over and over. In this scenario, since we've gone ahead and stored a reference to an enemy, if we needed to do other enemy things, like the enemy take damage, we could turn right around and say enemy.take damage, and we've still only performed one conversion.
That's right. And then you just work with the new variable that you have through as many different member references as you need to make. So very good stuff. This really is an important concept, and I'm sure with this explanation that there are some of you that are watching this going, okay, I'm a bit confused. The bottom line is this. As we start writing sophisticated games or sophisticated applications, there are going to end up being methods that are going to take in a higher level class type. You're going to end up needing to cast your object back to that class type to be able to send it in to be operated on. That's one example. Another example that we're going to be using real soon is a hierarchy that starts with an actor and works its way down through all the way to an enemy or whatever. But we will contain all of the actors in the game in a list, which means as we start walking through all of those actors, we're going to need to check, hey, are you an enemy? Hey, are you a player? So that we can do specific things with them. So even though we're still pointing to the entire instance, the entire object, using this cast allows us to control the scope of what we see inside of it at that particular moment, depending on the type of variable that we're using. So it really is different than a lot of books out there say, or several books, where they're talking about a new reference gets assigned. It's not a new reference. The reference, as you've already seen through Logan's use of the object's reference equals method, reference is indeed the same. It still points to the object as demonstrated back here. Boom. So we're still pointing to the overall. So this guy points to the overall object, and this guy points to the overall object. It's just scope based off of type is being limited inside. That's the key thing here, inside. So are we pointing to enemy? If we're pointing to enemy, that means it's an enemy type, and we can see everything back up the hierarchy. If we're a game item type, we can only see game item. We can't see enemy now. We only see game item and everything before it. So we're limiting our scope. But this is something that we will begin using a lot. So if you feel it's a little bit confused, watch the video again. And then as we start progressing into real-world examples by creating games and all, you're going to get a good feel for this. I'm really confident of that. And Logan, anything else you want to add to that?
Just going back to the idea that it is the same instance, and that's shown that even though we took enemy and put it in game item, we still had the facilities to operate upon that game item, because we could have been, I guess, in an entirely a different class or a different assembly, and we could have taken in that game item. We have the facilities provided to us so that we can analyze that game item and see what it actually is, to be able to detect the fact that it is indeed an enemy. And after we've done that check, we can go so far as to actually take and cast it over to a real actual enemy, so no information has been lost. We have only changed what we can see at certain levels.
Right. Okay. Anything else?
No, that's all I can think of.
All right, so let's go ahead. See how much damage we have done. Doom, 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 doom. I say we've done a really good job. All right, so let's go ahead and go back to the very first whiteboard. All right, ladies and gentlemen, let's go ahead and come over here. And that takes care of casting. It has been a long ride, but I hope you have got a lot out of it. This is a very important video. Inheritance is a very important concept. In this video, we took a look at what inheritance is, We told you why you'd want to use it and demonstrated it numerous times. We took a look at the syntax. We introduced you to various terms that you're going to hear often when dealing with inheritance. We talked about the importance of member accessibility. Your members must be accessible to derived classes if you want them to be inherited. We took a look at constructor chaining. We saw how the execution worked and parameter passing and how parameters are required, or when they are required, they must be sent to the initializer. We quickly threw this in as a little bit of extra, talking about explicitly accessing base members that have been hidden. And we wrapped the entire thing up with a look at how we can cast from a derived type back to a base type, or from a base type to a derived type. And we talked about how it can be done implicitly or explicitly. And if you have to do it explicitly because we're casting toward the derived type, you must exercise caution so that you do not throw an exception because we ended up casting something that should not have been casted over to that particular type. And we've given you two new operators, the is operator and the as operator, to help simplify everything. So that is inheritance in a nutshell. And at this point, we're going to begin using it a lot. Now in the next video, we're going to start taking a look at virtual methods, and we're really going to start making use of polymorphism. When we get into this coupled with inheritance really does open up a wide range of things that we can start doing. So that means our knowledge reviews can start getting very interesting quickly. So with that, Logan, a big thank you to you. And that wraps up this video on inheritance. Thank you a lot. We'll see you.